distinguished guests, resource persons, participants, Assalamu alaikum and a very good morning to you all. On behalf of OIC Comstech, we would like to welcome you all to the inaugural session of the International Training Workshop on Quantum Computing and Quantum Information. This training will be conducted from 11th, which is today, all the way till 15th of May. And we will start off firstly with the inaugural session. So, to formally begin the inaugural session for today, we will start with the recitation of the Holy Quran.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم الرحمن علم القرآن خلق الإنسان علمه البيان الشمس والقمر بحسبان والنجم والشجر يسجدان والسماء رفعها ووضع الميزان ألا تطغوا في الميزان وأقيموا الوزن بالقسط ولا تخسروا الميزان صدق الله العظيم.
Now, up next, we have the recorded message, the welcome remarks from the Coordinator General OIC Comstech, His Excellency Professor Dr. Muhammad Iqbal Chaudhary.
أعوذ بالله من الشيطان الرجيم. Bismillah ar-Rahman ar-Rahim. First, Dr. Sayyid Kumail Tayyibi, President, Eco-Science Foundation, Guest of Honor. Guest of Honor was Dr. Zafar Nawaz Jaspal, Acting Vice Chancellor of Quaid-e-Azam University, resource persons, ambassadors, distinguished guests, ladies and gentlemen, Assalamu alaikum, and very good morning to all of you. It is a great pleasure for me to welcome you to the International Training Workshop on Quantum Computing and Quantum Information. This is a very important event which is jointly organized by OIC Comstech, Center for Training and Research at AI and Emerging Technologies, and Comstech Huawei ICT Academy. We are extremely grateful for the valuable contributions of our resource persons who have developed the content for the training and will impart this training module during 11th to 15th May. Ladies and gentlemen, this training workshop has a participation of over 18 OIC member states, with physical and virtual participants from Azerbaijan, Bangladesh, Burkina Faso, Cameroon, China, Egypt, Gambia, Indonesia, Kenya, Jordan, Malaysia, Nigeria, Pakistan, Saudi Arabia, Sudan, Togo, Tunisia, and Yemen. The presence reflects a shared commitment to advancing science through cooperation, knowledge exchange, and collective progress. This workshop brings together academics, industry professionals, and emerging young researchers. The diversity of participation is one of the workshop's greatest strengths and will ensure rich discussion and innovative perspectives. Ladies and gentlemen, human history has repeatedly been shaped by scientific revolutions. From the industrial age to digital era, today we stand at the threshold of another profound transformation driven by quantum science and technology. Quantum computing, quantum communication, and quantum sensing promise capabilities that were once considered impossible. These include secure communication systems, revolutionary advances in artificial intelligence, breakthroughs in material and energy technologies, and accelerated discovery in medicine and industry. However, the true strength of our technological revolution lies not only in innovation but in inclusion. It is essential that developing nations participate actively in shaping the quantum future. Building human capacity, strengthening research institutions, and empowering young scientists are critical steps to ensure that no country and no community is left behind in this very important technological paradigm shift. This five day training workshop represents an important investment in the future. By bringing together students, researchers, and professionals from diverse scientific backgrounds, the program promotes learning, collaboration, and sharing of expertise across the borders. The workshop includes foundational lectures, technical training, and hands-on experience. This will help nurture a new generation of scientists equipped to contribute in emerging quantum technologies. Science today transcends geographical and political boundaries. Ideas move freely across continents, and collaboration has become the cornerstone of innovation. Initiatives such as this strengthen scientific diplomacy and foster partnerships that benefit humanity as a whole. Through these efforts, OIC Comstech, the Ministerial Standing Committee for Science and Technology Cooperation for 57 member states and 5 observer states, committed to empower OIC member states in a strategic and sustainable manner. OIC Comstech work in AI, cybersecurity, and emerging technologies. Comstech has actively working to advance digital transformation agenda within OIC member states. Allow me to highlight some of these key initiatives. OIC Comstech has been entrusted with the responsibility to develop OIC-wide AI vision aimed at guiding member states in policy development, ethical governance, capacity building, and responsible adoption of advanced technologies such as AI. Dedicated OIC Center of Excellence for Training and Research in AI and Emerging Technologies is becoming the hub of training and capacity building for the entire OIC region. Over the past years, OIC Comstech has organized numerous international workshops, exhibitions, hackathons, and capacity building programs in areas such as AI, blockchain systems, cybersecurity, and smart technologies. These initiatives have facilitated thousands of young scientists and professionals in 52 countries to acquire advanced digital skills. Together, let us work towards building an OIC community that is technologically empowered and capable of shaping its own future in this rapidly changing world. At the end, I wish all participants a productive and successful program. Thank you very much. Assalamu alaikum wa rahmatullahi wa barakatuh.
Up next, for the introduction of the training course, I would like to invite Professor Dr. Farhan Saab, who is the consultant on basic sciences at the OIC Comstech. Please welcome, sir.
Bismillahirrahmanirrahim. Assalamu alaikum. Honorable Coordinator General of Comstech, Professor Dr. Chaudhry, distinguished scholars, scientists, researchers, respected guests, participants from OIS member states, ladies and gentlemen, Assalamu alaikum. I would like to begin by appreciating the visionary role of Comstech leadership in promoting science, technology, and academic collaboration among the member of the states of Organization of Islamic Cooperation. The International Training Workshop on Quantum Computing and Quantum Information is an example of this true leadership. At a time when the world is entering a new technological era, such initiatives are not only valuable, but essential for future strength and progress of Muslim Ummah. By the grace of Almighty Allah, we are showing our dominance on our enemies and celebrating technological advancement as Mark I had today on our success in Brianna Versus. It's imperative to make ourselves advance in the leading quantum technologies and relevant areas in that sense as well. Major global power have already recognized the strategic importance of these technologies. In 2018, President Trump dedicated $1.2 billion to boost quantum technologies. In 2025, the US Department of Energy announced an additional funding to put US $625 million for national quantum research centers. Overall, the United States has launched more than 52 federal quantum initiatives involving government laboratories, universities, private industry to maintain leadership in quantum computing, sensing, communication. China, on the other hand, has moved aggressively from research towards commercialization. According to a recent industry report, China quantum computing industry reached approximately 1.61 billion in 2025 with annual growth of 30%. China has successfully established major quantum industrial clusters in Hefei, Beijing, and Shanghai. Most importantly, China has already begun commercial sale of quantum computers. Its neutral atom-based quantum computer entered commercial development in 2025, and sales exceeding 40 million yuan have been reported. And Pakistan is also one of the buyers of this technology here. China is also rapidly advancing high-performance quantum processors. Europe is similarly investing heavily in quantum technologies, particularly in quantum sensing, navigation, and secure communication. European strategic program are exploring integration of quantum sensors into advanced Air Force and aerospace technologies to improve navigation, stealth detection, and battlefield awareness. These developments clearly indicate that quantum technology are no longer theoretical concepts confined in laboratories. Rather, they are becoming instruments of economic strength, scientific sovereignty, and national security. For Pakistan, this is therefore the right moment to launch a serious national initiative supported by a strong political will and visionary governance. Such an initiative is essential not only for national security but also for scientific progress, economic growth, technological independence, and future competitiveness. For OIC countries in general, this movement presents both a challenge and an opportunity. Either we become active participants in this transformation, or we risk being left behind in a new era of scientific inequality. Talking about quantum technologies, they represent one of the most transformative scientific advancements of our time. These technologies leverage the extraordinary principle of quantum mechanics and perform unprecedented power and precision. Quantum technologies are expected to transform medical science, chemistry, climate modeling, finance, financial system, precision navigation, and space technology as well. Entirely new scientific fields are emerging as a result of this revolution, including atomtronics, spintronics, quantum photonics, and precision quantum sensing. These technologies leverage qubits and quantum phenomena, such as proposition and entanglement, to perform computation and measurements with unprecedented speed and accuracy. Therefore, building human capital, strengthening research capabilities, and fostering international collaboration are critical to ensure that developing countries are not left behind in this emerging technological revolution. The first step toward this goal is spreading quantum literacy and developing a foundational understanding of quantum concepts among students, researchers, educators, and professionals. In this context, the training workshop on quantum computing and quantum information has been organized with the aim of building foundation knowledge, practical skills, and collaborative networks among participants who are coming from science, technology, various different scientific fields, and mathematical sciences. Approximately 60 participants are joining physically, while around 300 participants from OIC countries and other parts of the world are joining online during this 5-day workshop. The workshop include sessions focused on both general awareness and advanced technical skills, along with hands-on practical experience. Distinguished international speakers will share their experience, expertise, and explain the profound impact quantum technologies are expected to have on our societies, economies, industries, and future generations. Our trainers include Dr. Razak, Dr. Hamad, Dr. Sabi, Dr. Badia, Dr. Sarah, and Ms. Mariam. So we have a very busy 5 days working on these in the training workshop. So I submit my thanks. And
Thank you very much, sir, for introducing the area of quantum computing and quantum information to our participants and explaining the format of the training that will be held over the 5 days. Up next, for a keynote, I would like to invite Mr. Arsalan Ahmed Khan, who is the Senior Solutions Manager, Cloud Computing Division at Huawei Technologies, Pakistan. Welcome, sir.
Thank you very much. Distinguished guests, partners, innovators, and my friends, Assalamu alaikum. It is a pleasure to speak with you today about the remarkable journey and the future vision of Huawei Cloud Computing Division, a driving force behind intelligent transformation across industries worldwide. We are living in an era where cloud computing is no longer optional. Rather, it is the digital backbone of governments, enterprises, and startups alike. The question is no longer should we move to the cloud, rather, how quickly we can innovate once we are there. So, here the Huawei Cloud sits at the forefront. Huawei Cloud Computing Division plays a pivotal role in accelerating the global digital transformation by providing a comprehensive, intelligent cloud foundation for enterprises, governments, and startups. Built on the vision of everything as a service, intelligence everywhere, Huawei Cloud delivers scalable, secure, and AI-driven solutions that empowers organizations to innovate faster and operate more efficiently. Huawei Cloud offers full stack capabilities across infrastructure as a service, where we provide the hardware which can be rented by the organizations to build their data centers. Then we have platform as a service where you do not need to worry about the underlying hardware and you can launch your services very quickly. The last is software as a service. We also have solutions for the developers who can want to launch their softwares quickly based on the data center technology. So the whole infrastructure portfolio includes our elastic computing. We have very strong compute servers up to 128 cores, and with hyper-threading technologies, we provide high efficient compute servers with even with the AI chips now already embedded in them. Then we have high performance storages and advanced networking solutions, software defined networks, which can quickly provide you all the requisite technologies which are necessary to drive this AI driven technologies. And we have a very globally distributed data centers as well. So at the platform level, if we talk, we have the cloud native developments, we have the container service architectures, DevOps integrations, and database solutions to support the agile digital operations. AI and big data services further enhance business intelligence through real-time analytics, machine learning platforms, and data-driven insights. A key differentiator of Huawei Cloud is its industry-specific approach. We have the tailored solutions for all the industry portfolios, including governments, banks, manufacturing, retail and energy, supporting the initiatives such as smart cities, digital banking, intelligent manufacturing, and modern enterprise ecosystems. By integrating cloud computing, AI, and IoT technologies, Huawei Cloud ensures that innovation is practical, scalable, and impactful. One important thing is the security. Security and trust are embedded into the architecture of Huawei Cloud with end-to-end encryption, AI-driven threat detection, zero trust frameworks, and continuous compliance monitoring. Additionally, the division emphasizes sustainability through green data centers, energy efficient workloads, and carbon optimization strategies. Looking ahead, Huawei Cloud continues investing in emerging technologies such as AI foundation models, edge cloud collaboration, distributed cloud computing, and digital twin solutions. Its mission remains clear: to build the digital foundation for an intelligent world and lead the next phase of cloud powered innovations. Thank you.
Thank you very much, sir, for introducing Huawei and the various products and services that you currently have in the domain of quantum computing. Up next, I have the honor to invite the guest of honor for today, Professor Dr. Syed Kumail Tayyibi, who is the president of EcoScience Foundation. Welcome, sir.
Bismillah ar-Rahman ar-Rahim. Professor Nasir Mahmood Khan, Sir Salam, Professor Farhan Said. Assalamu alaikum and very good morning. It is a great pleasure for me to join you today at this important training workshop on quantum computing and quantum information, advancing the OIC quantum frontiers at comstech. At the outset, on behalf of the EcoScience Foundation and on my personal behalf, I would like to sincerely congratulate comstech, Qaid Azam University, and Hawaii Technology for organizing this highly relevant training workshop. I would also like to appreciate Professor Dr. Farhan Said and all those who have contributed to bringing together scholars, experts, and technology partners around this important subject. Dear colleagues, dear participants around the world, frontier technology are reshaping the future of economies, industries, societies, and even national security. Artificial intelligence, biotechnology, advanced materials, clean energy technologies, and now quantum technologies are refining what countries can achieve and also what they may lose if they remain behind. Hence, this workshop comes at the right time. Quantum computing and quantum information are not just another academic field. They present a new scientific and technological frontier. Their long-term implications may be profound for computing power, secure communications, cybersecurity, sensing technologies, material discovery, drug development, climate modeling, and many other areas that are crucial for human development. Of course, quantum science is highly specialized. Many of us are not quantum physics, and we do not need to pretend that we are. But as leaders of science institutions, universities, and policy platforms, we must understand one thing clearly. Quantum technologies are likely to become strategically important in the coming decade. Therefore, our countries cannot afford to remain unaware, unprepared, or absent from this conversation. Ladies and gentlemen, for developing countries, including many countries in the OIC and ECO regions, the question is not whether we can build the most advanced quantum computers tomorrow. That would be unrealistic. The real question is, are we preparing our young people, our universities, our research institutions, and our policy system to understand and participate in this emerging technology revolution? This is where we must begin with human capital. We need students who understand the fundamental. We need young researchers who can connect physics, mathematics, computer sciences, engineering, cybersecurity, and information technology. We need faculty members who can teach emerging subjects with confidence. We need regional networks where experts can share knowledge. We need access to online platforms, cloud-based quantum tools, training programs, and collaborative research opportunities. In other words, before we think about very expensive infrastructure, we must first build quantum literacy, scientific curiosity, and research readiness. Dear colleagues, this is very critical because the developing world has often entered previous industrial revolutions too late. In many cases, we have become users of technology developed elsewhere. We purchase the products, we adopt the platforms, we consume the system, but we did not always build enough capacity to become creators, innovators, manufacturers, or knowledge leaders. We must not repeat this pattern again. For the OIC and ECO region, this is an opportunity, as Professor Chadri and other colleagues just mentioning. This is an opportunity for deeper cooperation. No single developing countries can build a complete quantum ecosystem alone. But together, we can create a strong foundation. We can share experience. We can connect universities. We can support visiting fellowships. We can organize regional training workshops. We need faculty members who can teach emerging subjects with confidence. We need regional networks where experts can share knowledge, in access to online platform, cloud-based quantum tools, training programs, and collaborative research opportunities. This is where organizations like comstech, and ECUSF have a significant role to play. Dear participants, another important point is youth engagement. The future of quantum science in our region will not be only by senior scientists. It will be built by students who are sitting in classroom today. It will be built by young researchers who are willing to enter difficult fields. It will be built by those who are not afraid of mathematics, coding, physics, and experimentation. Therefore, we must make frontier science attractive and essential, accessible to young people. This could only become possible if we democratize access to knowledge. We can create a much larger pool of talent. I would conclude by experience my strong appreciation for this interactive initiative. ECOSF stands ready to support regional science diplomacy and capacity building in frontier technology. I am confident that this workshop will inspire many young minds to explore quantum science, ask bold questions, and pursue excellence in frontier technologies. Thank you very much.
Thank you very much, Professor Dr. Said Tayyib. I just want to convey that in our next 5 days, we have 6 speakers with us. There are 2 international speakers who will be joining, one from USA, Professor Zuberi, and then we have Professor Dieter, he's from Germany, and at the moment he is in China. So these 2 talks will be on general awareness, at the same time explaining the latest development in quantum information and quantum computing. And then it is my talk where I will also explain the latest fundamental concepts in quantum computing and also connecting them into the applications where we can apply. In our next days, we are going to talk about the mathematical foundations first. We have a very excellent speakers on these topics. Professor Zach is there, and then we have Hamasa. He would be explaining these topics, and then we shall be having a discussion on quantum algorithms. And then Dr. Sarah Vedat is going to explain, and then we have also Dr. Sabi is going to explain us about quantum information as well. So this is a simple introduction of our 5 days activity. Together with that, we shall also have hands-on experience. So you should prepare your laptops. We shall help you in getting the appropriate software on your laptop, and then we shall be providing some basic understanding how you can build some simple small circuits on your computers. So this way, let's hope for a very positive environment and activity. Thank you.
Thank you very much, sir, for briefing the participants over the 5 days how we will structure this training sessions. And I would like to once again thank our guest of honor for your presence here today and for gracing this occasion. So up next, now we'll move on to the technical session of the training, and we'll start with the technical talk. So we'll just take a couple of minutes and we'll move on to our first speaker. Assalamu alaikum. Apologies for the delay, for the technical glitch. We were trying to get this copied and we had some issues. So we'll start off the technical session, and the first one is from Professor Dr. Sohail Zubairi, who is a distinguished professor at the Texas A&M University, United States of America. And the topic of his talk is quantum communication, optical communication with invisible photons. So this presentation is a pre-recorded presentation. So we'll be playing that now.
This talk is about quantum communication. This is an area that is gaining more and more importance with the passage of time. My talk will be divided into two parts. In the first part, I'll give you sort of a tutorial of quantum communication. And then in the second part, I'll talk about some work that we have done in the field of counterfactual communication. So quantum communication basically goes back almost 40 years. The first protocol that was suggested was in 1984 by Bennett and Brassard, one of the most popular protocols for quantum key distribution. The main objective of quantum communication has been secure communication, and there have been several protocols like B92, Eckert 91, and so on and so on. One thing which is common to all of these protocols is that these quantum key distribution schemes, they require real information carriers, a classical channel, and a probabilistic outcome. We will see a glimpse of it when we discuss BB84 a few minutes later. Okay, the question that we address in this presentation is, can we come up with a quantum communication protocol that involves direct communication? So that means that there is no need for a prior quantum distribution, and no information carriers in the public channel, and no classical channel needed for communication. So now this looks like a very difficult job, almost impossible job of having a direct communication, but with no information carriers in the public channel. This will be the second part of our talk. So the organization is something like this, that I'll first present some ideas about the elements of quantum cryptography. Then I'll talk about this scheme, which is used very extensively right now in our e-commerce. When we send some information electronically, this is the protocol that we use, and I'll give you some details about it. And then I'll talk about this BB84, which I just mentioned. And then the second part will consist of direct communication with invisible photons. And I'll start with some very basics, describe Mach-Zehnder interferometer, describe what is interaction-free measurement, and then talk about counterfactual communication. Okay, so let's start with cryptography. This is a subject which is thousands of years old, and the objective of cryptography is that we would like to communicate two parties would like to communicate in absolute security, security. And the way it is done is that if a message is to be sent, it is encoded with a key. So the message that is sent between two parties is essentially a message which is incomprehensible, like what you're seeing here right now. However, if I use a key to encode it, I mean, the key in this case is a very simple one. Just a letter is shifted by one, A goes to Z and B goes to A, C goes to B, etc. Then J becomes I and B becomes A and N becomes M and so on. And once we do that, then we have the actual message that we intended to send. So this is the intended message that we wanted to send, and this is the actual message which is sent, which can be decoded with the key. So the problem of cryptography is to make a key such that secure communication can take place. There are, however, two distinct problems with this kind of cryptography, which existed almost until early 1970s, going back thousands of years until very recent times. The problem with this kind of old-fashioned cryptography is that the sender and receiver should exchange key through secure channels. They cannot be exchanged on a fiber optics cables or any channel which is accessible to an adversary. So what that means is that maybe sender and receiver should get together, exchange the key, and then go apart and then communicate. But that would be very cumbersome, as we can imagine. The second problem is that it is possible for a clever eavesdropper to learn the key without the knowledge of the sender and receiver. So here we have this very simple key, and we communicate using this simple key. But it is quite possible that somebody who has access to this transmission channel could figure out, looking at these messages, looking at the actual information that is being sent, figure out what the key is, and then figure out what the message is. And this can happen without us knowing anything about it. So this is another problem. Well, in the public key system, which we use every day these days, the so-called RSA, there the sender and receiver exchange key on public channels. But the problem is that in this case, ultimate security is not guaranteed. So there is the good news and there is the bad news. I'll discuss RSA briefly in a minute. So now the challenge is, if we can have a protocol where key is exchanged on public channel or ordinary fiber optics cables or a telephone line, and if there is an eavesdropper that can be traced immediately. Now this, as we can see, appears to be an almost impossible problem. But it turns out that quantum mechanics can do the job. And this is, again, something I would like to discuss shortly. Okay, in the public key system, this RSA that we use, this is sort of the schematics. By the way, RSA stands the initials of three scientists, Rivest, Shamir, and Elderman, who came up with this idea in early 70s. And now it is used completely quite extensively. For example, when we send our credit card information on the internet, we feel very secure that somehow nobody is going to get access to it, even though it is being sent on public communication channels like optical fibers. And the reason is because of this encoding using RSA public key system. And the way it works is like this, that if I want to communicate with a large number of people, what I do is that I make an encryption key, which I send to all of these people on a public channel. As a matter of fact, I mean, this encryption key I can put even on internet on my website. And then what happens is that when one of these, for example, B1, wants to send me a message, which would be a number, I mean, number carries information, that would be encoded with this E and N. And then when it comes to me, then I decode it with another key, which I've kept secret from everyone, DN. And the nice thing about this scheme is that when this message is being sent, this is all being done on a public channel, fiber optics lines, for example. This encoded message, none of them is able to figure out what the message is. And the way it is done is that we start with, I start with 2 primes, P and Q, presumably very large prime numbers. Product is N, so that is this N that I mentioned here. Typically, N is a 256-digit number. And then it turns out that from N, P, and Q, I can generate 2 numbers in a manner that I describe in a second. And then this E and N, this I send to all the people with whom I want to communicate. And the decryption key, D and N, that I keep to myself. So D is not known to anybody, but E is. Okay, the way it works is like this. That the public key is formed in this way, that N is equal to P times Q. E is the encryption key, which is a number which is relatively prime to P minus 1, Q minus 1. The private key is found from this relation, DE modulo P minus 1, Q minus 1 equal to 1. The definition of modulo is that it is like if I divide 13 by 6, the remainder equal to 1. So this way I find out what D is. So E is something that I chose randomly, a number which is prime to, relatively prime to P minus 1, Q minus 1. Now E and N is the key. Now the nice thing about this protocol is that if I want to send a message, which is a number M, so you want to send me a message, this number M, then you would encrypt it through this relation. You would raise M raised power E. You know what E is, encryption key modulo N. And this is now a number which has no relationship, which has no apparent relationship to M. And this is sent to me. At my end, and this is the key, this is really the important point, that at my end, I have the decryption key. And then if I take this received message, which is C raised power D modulo N, I recover the message. So just to indicate to you, let me do an example. So P and Q, I choose 47, 71. Typically, they are very large number, but here I choose them very small numbers. N is the product of these 2 numbers. P minus 1, Q minus 1 is this number 3220. And then I choose a random number E as my encryption key, which is co-prime with P minus 1, Q minus 1. And then through this relation, I can find out what D is. So now it is D, which is the decryption key. And if I want to send a message, and here it is a numerical message, let's say 688, then the number that I sent is not 688, but rather 688 raised power this encryption key 79 raised power 79 modulo this N, which is 3337, and this is the number. So instead of M, you would be sending me this number, which has been coded with this encryption key. And at my end, I have this decryption key 1019. So through this relation, I recover the message. The amazing thing is that if in this case, everybody is listening to the message. Everybody, this message C is being sent on a public channel, and everybody knows what the encryption key is, 79 and 3337 in this case, but they cannot decipher what the message is unless they are able to factorize this n. If they can find out P and Q, then the code is broken and somebody can find out what message is being sent. It turns out that this is a highly difficult problem. I mean, multiplying two numbers is a very simple problem, but factorizing, find the factors of a large number, prime factors, this is a very difficult problem. As a matter of fact, for 256-digit numbers, on the fastest computer available today, it would take several decades before the computer can figure out what these prime factors are. So this is the essence of RSA encryption. Now, but again, as I mentioned before, there is a possibility that somebody can find out these factors, P and Q of n, and break the code. Now we would like to talk about a code, a quantum key distribution, which is unbreakable. And here I give this example of this Bennett-Bresser protocol of 1984. Okay, so here, first of all, just to point out how the communication goes on, as I mentioned already, the information is being sent in numbers, a sequence of numbers. Well, it turns out that the best numbers for communication are binary numbers, zeros and ones. So, for example, in this case, Alice wants to send this message, which is consisting of a string of zeros and ones, and they may contain information about, whatever Alice wants to tell Bob. But this is not the message which is sent on this public channel. It is a scrambled message, and the way it is scrambled is that we make a key which is known only to Alice and Bob, supposedly. And then this message and key, they are added. So now we have this scrambled message, okay? And this scrambled message is now sent to Bob. So Bob receives this scrambled message, and Bob has the key as well. And now he adds the scrambled message to the key and recovers this original message. So this is how the secure communication is done. And we can see that the important point here is to develop a key between Alice and Bob, which is secure. So, I mean, now this key has to satisfy two criteria. One of them is that it is developed on a public channel. I mean, we can be very, very far away, thousands of miles away. So it should be developed on these public channels like fiber optics cables, etc., which are accessible to any eavesdropper, for example. And the second thing is that if there is an eavesdropper trying to find out what this key is, we should be able to find out. Okay, now this is done through this protocol, that VB84, and it turns out that it is based upon some very simple ideas. I mean, this is an almost impossible task, but it is based on just this principle of complementarity, which goes back to Niels Bohr. And what it says is that two observables are complementary if precise knowledge of one of them implies all possible outcomes of measuring the other one are equally probable. Okay, so here is an example. So for example, I mean, here I take the example of polarization. So supposing I consider a single photon, and single photon has a polarization in the vertical direction. Okay, so this is a photon which is polarized in the vertical direction. And now we ask the question, what happens if this photon passes through a polarizer oriented at 45 degrees, or polarizing beam splitter, let's say, oriented at 45 degrees? That means that now the possibility for this photon, which is vertically polarized, is to go through either 45 degrees or 135 degrees. Well, it turns out, as we can imagine, that there is an equal probability to go through 45 degrees or 135 degrees. Okay? And this is essentially what we are talking about is Bohr's principle of complementarity, that if I make a measurement in this basis, vertical or horizontal, then if I try to measure it in a polarizer which is rotated by 45 degrees, then the outcomes become equally probable. Same thing goes with this photon, which is polarized, let's say at 45 degrees. If I try to look at it in this polarizing beam splitter, which is able to see it in horizontally or vertically, then through this decomposition, we can see that the probability of finding it in vertical polarization or horizontal polarization, they are equal, and so equal probability for both of them. This is all that is needed in order to understand quantum cryptography. Okay, so here is now the protocol, just based upon what I explained on the last view graph. So here I developed some notation. So I would describe two bases for polarization. I will call it plus basis and I'll call it X basis. Plus basis means that I can send my photon in along horizontal or vertical, 0 or 90 degrees. 0 degrees will correspond to a logic 0, 90 degrees will correspond to logic 1. Or I can send it in X basis. So that means that I can send it either 45 degrees or 135 degrees. 45 degree I'll call 0 and 135 degree 1. And now I can state what I just explained, that this is Bohr's principle of complementarity essentially. If polarization is measured in one basis, let's say plus basis, then the possible outcomes of polarization measurement in the conjugate basis is equally probable for the two directions. That is now all that is needed. And how the quantum key is made between Alice and Bob. So Alice basically chooses different orientations for the polarizers, plus, X, 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 plus, and so on. So here I give the example with 9 photons. She chooses different particular orientations. So in X, there is a possibility 0 and 90. She chooses 0. So here at 90. Here there are two possibilities, 45, 135 degrees. So she chooses 45 and so on. And they correspond to zeros, and 45 corresponds to zeros, and 90 degree and 135 degrees correspond to ones. So this is what Alice sends to Bob, okay, using this basis. Now Bob is sitting thousands of miles away, doesn't know what Alice has chosen. So he chooses, he tries to measure the polarization of these photons by choosing different bases at his end. So for example, the first photon he measures with plus basis, the second one with X basis, third one with plus basis, and so on, so on. Well, it turns out that if the basis chosen by Alice and Bob is the same, then Bob will get the same state of polarization that Alice sent. So in this case, it will be 0 degree sent, 0 degree received. But if it was sent with a plus basis, but received with X basis, then Bohr's principle of complementarity tells us that there is an equal probability that it will be received either at 45 degrees or 135 degrees. Here again, the two possibilities have equal probabilities and so on. Now at this point, Alice and Bob can communicate through a classical channel and compare the basis that they had chosen, not the outcomes, but the basis. So Alice says, oh, I sent plus basis. What did you have? Bob says, I had plus basis. So they decide to keep this outcome. Alice says, the second photon I sent in plus basis. What basis did you choose? And Bob says, I choose X basis. They throw away this one because there is no guarantee that it reached in the same polarization, and so on. And then they keep these ones where the bases were the same, and this becomes their key. Okay, so this is how keys formed on a public channel. Now, how is it secure? I mean, if there is an eavesdropper, how is it that eavesdropper has no access to it? Well, eavesdropper, so here I give an example of, let's say, a photon which is sent in plus basis, let's say at 0 degrees, and received in a plus basis. Eve is somewhere in between these thousands of miles. Now, Eve doesn't know what basis Alice and Bob has chosen. They They reveal their disjoist after the measurements have been done. So while it is passing through Eve, she doesn't know what polarization was chosen. So Eve has two possibilities. Either she chooses the correct one or she chooses the wrong one. Okay, so now in the case of correct one, which happens roughly speaking 50% of the time, she really figures out what Alice wanted to send. But in those cases where she chooses the wrong one, then there is an equal probability that Bob will get the correct answer, and 25% of the time that he will get a wrong answer. So now what Alice and Bob can do in order to find out whether Eve is there, they could choose part of their outcomes of the photons and compare the outcomes. So Alice says, I sent a 0. What did you get? So Bob says, I get a 0. So they say, okay, that's good. But if it turns out that in their comparison, roughly speaking, 25% times Alice and Bob's outcomes are different, then they are sure that somebody is trying to listen to it. Eve is there. And then they can abandon this key and try to form it again. So this sort of indicates that both objectives have been achieved. That is that a key has been exchanged on a public channel, but if an eavesdropper is present, she can be identified. One of the major experiments that was done recently in China, they basically implemented this very simple scheme, theoretically very simple scheme through satellite. So basically from China, they sent a message through a satellite within China, about 2,500 kilometers. And in another experiment, they sent it to Austria, 7,600 kilometers to form this key and send actual messages using that key over these long distances. So for example, China, they sent a message encoded like what I just explained, the picture of their big optics hero from past, Miao Qi, and Austria sent the picture of their biggest hero, Erwin Schrödinger, using this BB-84. And this experiment really almost shook the political establishments all over the world. For example, this experiment, which was published in the summer of 2018, in the December 2018, President Trump signed a $1.2 billion law to boost quantum technology. And here he's talking about quantum computers and highly secure communication, and pointing out that this has been motivated by this leap by China. European Union also launched a 1 billion euros initiative in Europe and many other countries. So this had such an impact, but this has a lesson also for us that sometimes physics can be very, very simple, but very, very far-reaching consequences. Okay, so now let me move on to something that we did. That is that we looked at a slightly different problem in quantum communication. We asked the question, can we come up with a quantum communication protocol that involves direct communication, no key exchange? Direct, if I send you a 1, you receive it as a 1, and if I send you as a 0, you receive it as a 0. In such a way that there are no information carriers in the public channel, no photons there, and no classical channel. You and I do not have to communicate at the end using a classical channel in order to establish this, to transfer this information. Can we do that? So the idea is something like this, that here is Alice. She has an optical setup, which is represented by this black box. And she has 2 detectors, D1 and D2. And she has a photon source. And Bob has only a mirror. Okay. So now in this protocol, Bob is sending the information to Alice. The way it is done is that Alice sends a photon through this optical setup and then on to Bob. Now, Bob has two choices. Bob can either put his hand in front of the mirror, block it, or does not block it. Okay? If he blocks it, that may correspond to, let's say, logic 0. And if he does not block it, then that may correspond to logic 1. It turns out that if he blocks it, at Alice's end, detector D1 clicks. If he does not block it, then at Alice's end, D2 clicks. So by D1 clicks, Alice knows that Bob wanted to send a 0. Okay, and D2 clicks would indicate that Bob wanted to send a 1. The amazing thing of this protocol that we proposed is that if we try to find out photon in this transmission channel, it's not there. The probability of existing of this photon in this public channel is 0 in both instances. So it is somehow happening that this photon is bouncing back and forth through this Alice's apparatus and giving us a click at D1 or D2, depending upon what Bob is doing far away. Okay? So this would look quite strange. It is almost like psychic communication. Okay? But this is science, you know. I mean, we are talking. I mean, I'll give you an explanation how it can be done. So this is the essence of counterfactual communication. Counterfactual communication, I mean, this is essentially the optical setup that we had in mind. So as we can see that this is consisting of some very simple optical elements like polarizing beam splitters, switchable mirrors, optical delay lines, focal cell, and so on, so on. So this is the setup which gives us a click at D1 or D2 depending upon what Bob does here. And this work was done with some colleagues. As a student, Chenghong Li was my postdoc, and Alamri is one of my good friends from Saudi Arabia, and we published it many years ago. Created a lot of controversy, which unfortunately I won't have time to go through it, but I'll show you, you know, what people say today about this thing. Of course, this is a very complicated. I mean, this setup consists of these very simple optical elements, but in order to explain it, it becomes, you know, it's quite complicated. So I'll try to explain it at a level that we can all see it very, very clearly what's going on. Well, it turns out that the only thing I need to know is just this beam splitter. Okay, so here is a beam splitter on which a single photon is incident and no photon from the other side. And this I designate left photon 1 and right photon 0. And in the output, depending upon what the reflectivity is and the transmission, I mean, cosine theta happens to be the reflectivity. So that means that this is the amplitude which will be reflected. And sine theta corresponds to the transmittivity. So that will be the amplitude which will be transmitted, that no photon here and 1 photon here. So 1, 0 transforms this way, 0, 1 transforms this way. And it is, I mean, in the rest of my talk, this is all that I need to know, nothing else. And on that basis, I can explain optical communication with no photon in the transmission channel. Okay, so here I do it in step by step. So from one beam splitter, let me go to 2 beam splitters. So here I have one beam splitter, 1, 0, which undergoes this transmission according to what the reflectivity is. Theta is what defines what the reflectivity is. Here are these 2 mirrors, and then there is a beam splitter. Okay. And it turns out that if I apply this formula, which I showed you here, onto these 2 beam splitters, the outcome turns out to be equal to something like this. The other possibility is, so this is what we call Mach-Zehnder interferometer. The other possibility is that I have some blockade at this point on the right-hand side. And in this case, what happens is that 50% of the time it can sort of go transmitted, the photon gets transmitted, but then it is absorbed. and then 50% of the time it is reflected, but now there is no interference. And I get equal probability of getting it here and here. Okay? If we have 50-50 beam splitter, which I mentioned in a minute. Okay? So this is what the outcome will be. This cosine theta represents the probability. So the first one will be two reflections, cosine theta, 2 reflections. The second one will be cosine theta and cosine theta reflection and transmission. So this is 0, 1. Okay, this one we don't count. This is lost. Okay, so now if I have a 50-50 beam splitter that corresponds to theta equal to pi by 4, then it turns out that I'll get a click at D2 guaranteed, 100% probability. Here, so this is a result of quantum, result of interference. Here, on the other hand, I'll get, for this photon which is reflected, equal probability of getting a click at D1 and D2. Okay? So this is how we can look upon this. Okay, so this means that if I get a click at D2, then I do not know. I mean, so if I just sitting here, I do not know what is happening, in this region. Then if I get a click at D2, it could mean either there was no blockade like this, or it could be blockade because there is a probability that I get 25% probability of the click here. On the other hand, if I get a click at D1, then I know it cannot be this. It has to be this. That means that there was an object, an absorbing object in this setup. Okay. Now, this is the essence of interaction-free measurement, which has been, again, very well studied, goes back to Elitzur and Weidman many years ago. So the whole idea there is that if D2 clicks, we have no information. But if there is a D1 click, then we know that there was no object and we can find out the object. So in this case, we can detect the object without the photon interacting with the object. Typically, if I want to look at something, I will shine light upon it, and then the light will be scattered into my eyes or detector, any detector, but the photon interacts with the object. In this case, the photon is able to tell us whether the object was there or not, but without the photon interacting with the object. Okay, for those events where I have a D1 click. Okay, so this is the essence of interaction-free measurement. Okay, now let's complicate the system a little bit more. So we are gradually getting to our counterfactual communication. So in this case, we consider, for example, a set of n beam Mach-Zehnder interferometers. Reflectivity in this case, we do not choose as pi by 2, but rather pi over 2n. So now n is the only parameter which defines this setup. N has two meanings. N is the number of Mach-Zehnder interferometers, and n also corresponds to the reflectivity. Cosine of pi over 2n corresponds to the reflectivity. And similarly, transmittivity will be sine over pi over 2n. And if I send in a single photon, the same setup as before, then I can show by using this transformation that I mentioned before, the beam splitter transformation, that the photon will be detected at D2 with 100% probability. Okay. So this is basically after n cycles, and if I have this capital N, which happens to be equal to pi over 2 theta, and theta is equal to pi over 2, in that case I get a click at D2, 100% probability. Now let's analyze the second problem, where there is a blockade at every instance. Okay. I mean, right now we are not talking about our setup. Okay. That will come next step. But here we can see that if there is this setup, then what happens is, let me not go into these details, but we can see that as a matter of fact, if the reflectivity, if n happens to be very large, that means we have a very large reflectivity, very small transmission. So what happens is that in this case, we will get a reflection here with very small probabilities for the photon to go on the other side and get absorbed. So cosine theta, cosine theta, cosine theta, n times. And therefore the probability will be that it will be reflected here, and that goes like cosine 2n theta. And if n is very large, theta is equal to pi over 2n, then we know that this number approaches equal to 1. So with almost unit probability, I get a click at D1 if the photon is blocked at all these levels. Okay? This is, in some sense, a generalized version of the interaction-free measurement. Okay? So now just to summarize, if I have this setup, no blockade, I get a click at D2 with unit probability. And if I have a blockade at every step, then I have an almost unit probability at D1. This is all that we will use. And this was an experiment which was done by, everybody is very famous on this list, Paul Kuyat, Weinfurter, Herzog. It was done in Anton Zeilinger's lab with Mark Kezevich. Okay, so this was their experiment for interaction-free measurement. Okay, so now we come to the problem at hand, what we wanted to do. Can we come up with a quantum communication protocol that involves direct communication, no information carriers in the public channel, no classical channel? Okay. So for that purpose, we basically generalize the system that we just talked about. So we have essentially these n rays of Mach-Zehnder interferometers embedded into another set of m Mach-Zehnder interferometers, such that the left-hand side consists of these n Mach-Zehnder interferometers. Okay, everything in this setup, except for this mirror, these mirrors belong to Alice. These beam splitters, these beam splitters, these mirrors, all of them belong to Alice, and as well as these detectors. The only thing that Bob has is the mirror, which he can either block or unblock. So these two situations. And if he does not block at any stage, that corresponds to logic 0. If he blocks at every stage, that corresponds to logic 1. Okay. So now this whole system is defined by two numbers, n and m. N corresponds to the number of Mach-Zehnder interferometers here, and n also corresponds to cosine of pi over 2n corresponds to the reflectivity. Similarly, m corresponds to these outer Mach-Zehnder interferometers, and m also corresponds to the reflectivity cosine pi over 2n. Okay? So these two numbers basically define this rather complicated looking setup. Okay, but now let's see how we can accomplish counterfactual communication, which means no communication in the public channel, through this rather simple looking setup. Okay, a little excellent, but simple. Okay, so we can explain what happens through these figures. So this is what we have learned already, that if there was no blockade in this kind of setup, I'll get a click here. If there is a blockade, I'll get a click here. Now let's come back here and analyze the case when Bob does not block the photon, okay, at any stage. That is to say that Bob is trying to send a logic 0. What will Alice get here? Okay. Well, okay, so now we can see that actually most of the amplitude of the photon is being reflected. So I get this cosine of raised power m of pi over 2m, and that will give me a click with almost unit probability here. Supposing the photon leaks, there is a very tiny probability, but it can leak. Then this tells me, this picture tells me that it will be definitely detected at this detector here. It will not be able to come on the left-hand side to Alice again. So that means that if this photon is lost on the Bob side, then, okay, no information is transmitted. But when Alice receives the photon at detector D1, then she knows that Bob did not block the photon. Bob did not block it. He intended to send the logic 0. Please notice that in those events, which are very large, almost 99%, where Alice detects the photon at D1, the path that the photon takes is this outer path. Photon is never in this public channel, the channel that exists between Alice and Bob. Okay? So here we have a situation where Alice can find out whether the Bob unblocked, but in such a way that there is no photon in the public channel. Let's analyze the second situation where Bob blocks at every instant, basically signaling that he wants to send a logic 1. Now, in this case, again, we use this language, and I mean these systems that we have just understood. So in this case, again, there is one possibility here, but then there is this possibility that it can go, it can leak. When it leaks to the left-hand side, then it gets reflected. The situation is something like this. And then with almost unit probability, it enters in here again. So this is almost like the situation of an unblocked photon. And therefore, when we sum up everything, we see that the photon, like here, detected at D2, it is detected at D2. Okay? So even though this is a blocked configuration, but it behaves more like an unblocked situation here in this way that all the amplitude that comes in here enters on the left-hand side. Again, we can see that, for those photons that are detected at D2, there is no photon in the public channel. So now we have a situation where there is unblocked photon, click at D1, blocked photon, click at D2, no photon in the public channel here, no photon in the public channel here. So this is our scheme for the counterfactual communication, which we could explain using just this Mach-Zehnder interferometer and just using the property of the beam splitter. Okay, I mean, how about the success probabilities? And here, this red region corresponds to larger than 95% success. And we can see that and the only parameters that in the problem are N and M. And we can see that these N and M's for different values, we can actually get some very high success probabilities. Okay, now this may be a very cumbersome thing because the number of beam splitters could be very, very large. Can we fold them together? And that is this circuit, which I was hesitant to talk about before. But if we look at it very carefully, and again, since my time is almost up, therefore I'll not explain it, how this works. But this is, in some sense, a Michelson interferometer type configuration corresponding to these Mach-Zehnder type configuration with very limited number of resources here, but difficult to understand. More resources here, easy to understand. Okay, the experiment was done by in China by Jianwei Pan, the same group that did that experiment that I showed you before, which shook the political establishments all over the world. So he was the one who did this experiment in 2017. And basically, he could communicate this what they call in China some knot, through this counterfactual communication protocol to here. So here he talks about, intuition from our everyday lives give rise to the belief that information exchange between remote parties is carried by physical particles. Surprisingly, in a recent theoretical study points out to us, quantum mechanics was found to allow for communication even without the actual transmission of physical particles. This made, of course, headlines many places. So when Jianwei Pan's experiment came out, there was a story in Physics Today. It's difficult to grasp the implication of an experiment that seemingly sent data from Bob to Alice without any physical messenger passing through them. And he talked about our scheme was proposed at Texas A&M University, and Pan and colleagues experimentally verified this scheme. And there were many other stories at very many different places. But of course, this created, as you can imagine, a lot of controversy. Some people just did not like it, and they just thought that this was not possible. I wish I had time to give you some flavor of what the arguments was, but mostly they came from Weidmann, who I mentioned as the pioneer of interaction-free measurement. And Weidmann boss is, the senior person at his institute is Aharonov, Yakir Aharonov, a famous Bohm-Aharonov effect. And in December 2020, in this paper, this is how he started his paper. And let me put it in bold. So he mentions our paper, says, describes a remarkable effect which they call counterfactual quantum communication transmission across a transmission channel of information from a sender to a receiver without any physical particles traveling between them. For all our familiarity with quantum non-locality, the effect is startling. It involves neither non-local quantum correlations, which anyway do not transmit information, nor the relative phase of the Aharonov-Bohm effect. Remember, this paper is being written by Aharonov. If any effect evokes Einstein's famous phrase, spooky action at a distance, it is this one. So as you know, this sort of indicates how counterintuitive this result is.
So that was the first lecture, and what we'll do right now is we'll take our lunch and prayer break right now, and we'll resume with the remaining of the technical sessions at 1:45 sharp. So lunch is served here. My colleague will guide you. So please have a break at lunch, and then we resume here exactly at 1:45 for the next technical session. It will go up till 4 o'clock. Per month, right?
Hello, Professor Dieter. How are you? Hello,
I'm fine,
Professor.
thank you. How are you?
Can you hear me?
Yes,
Excellent, excellent. So should we start your presentation?
fine for me.
Yes.
Can you see the screen? Is it the right? No, I think this is the wrong screen, right?
We can see the screen
Which one?
with your presentation. Hybrid field quantum registers.
Yes, but I suspect it's the wrong one. Try again.
So you're at Hefe at the moment?
So you see the presenter screen or you see the full screen?
We can see only you now.
Okay, that is strange. And now?
It's still not shared. We don't see your presentation at the moment. Recording already. Okay.
And now?
No, not yet. Something puzzling.
Yep.
Right. Professor Dieter, may I introduce you at the moment?
Sure.
Okay. Well, we have our first speaker of the second session as Professor Dr. Dieter Sutter. He has been a professor of physics at Technical University Dortmund in Germany since 1995. He received his doctorate training at ETH Zurich under the supervision of Professor Richard Ernst, the 1991 Nobel laureate. Professor Sutter's research spans magnetic resonances, quantum information processing, and quantum sensing. He is widely recognized for his contributions to dynamical decoupling, pulse sequence techniques that protect quantum coherence from environmental noise. His group has also achieved a series of important results on the nitrogen vacancy centers in diamonds, including single spin quantum control, quantum memory, nanoscale temperature sensing, and noise protected quantum gate operators. His publication has been cited over 15,000 times on Google Scholar. So here we have Professor Sutter, so I invite him. Thank you.
Okay, thank you. Can you see now the presentation?
Yes, we can.
Okay, finally. All right. So let me start with introducing the place where I come from. As you hear, I was a professor of physics in Dortmund, and since I don't assume that all of you know where Dortmund is, here is a map of Western Europe and Germany, and the arrow points to the city of Dortmund. And you see here a picture from the center of Dortmund, and this is an aerial view of the campus of the university. Has a northern and a southern part, and down the lower part represents the math tower. And the university has about 35,000 students. In case anybody has heard about Dortmund, I assume it was not the university, but maybe some of you know what this stands for. That's the most favorite football club in the area. Usually these are the players in the black and yellow shirts. This is a scene from a game which was played in the US some years ago. And normally, Borussia Dortmund is the second team in the table just behind Bayern Munich. Right now, I'm not in Dortmund. I'm at the University of Science and Technology of China, which is in Hefei. Hefei is a small city in China, has about 8 million people, and it has an excellent university, which appears to be quite popular also for students from Pakistan. We have quite a number of students and applications from Pakistan. Yeah, so next I would like to mention a few of the research areas in which I have worked. As you heard from the introduction, I started out in magnetic resonance and then went into laser spectroscopy, or quantum optics, as it's sometimes called, and which is in some sense related to magnetic resonance. In particular, I like to combine magnetic resonance with laser spectroscopy. And that became very useful when the field of quantum information started out around, well, in the late 90s of the last century. And you see here some of the combinations of lasers and radio frequency microwaves that are used in this field. And finally, I had some projects in medical physics, for instance, on the human brain. Now, let's start with the quantum part, and I would like to briefly motivate why we are working on quanta. This should be quite popular now after the International Year of the Quantum, which celebrated 100 years of quantum theory last year and just ended a few weeks ago. So the probably most common application so far is actually in communication. Quantum technologies allow you to have secure connection between two parties, here called Alice and Bob, sender and receiver. The idea is you communicate with single photons. And if you do that properly, this is the so-called BB84 protocol, it allows you to have a secure exchange of a key, which means if somebody listens in, you will notice. And so you can avoid chatting to each other when the communication is not secure. And this has been a popular field. The first such communications were established around the year 2000 in Europe. And in the meantime, China has become a leader in this field, putting up, for instance, the so-called quantum satellite, which allows to have secure communication between two distant places on Earth. And they also set up a secure communication network on land here between the four cities of Shanghai, Hefei, Jinan, and Beijing. So communication with quanta is certainly an interesting part, but also for measurements, quantum systems are very useful. For instance, the best time standards now use quantum technologies, and of course, sensing, for instance, magnetic fields or temperature or electrical field pressure and whatnot. Now, let me switch now to a different topic. Well, it's still based on quanta, but about quantum information and quantum computing. So to go back a little bit in history, the first electronic computers were built in the 1940s, like here, this ENIAC 1, which was designed and built in the United States. It had a weight of some 30 tons, covered an area of 160 square meters, used 20,000 vacuum tubes, 6,000 manual switches, and consumed 150 kilowatt of electrical power. Its computational power was, of course, a fraction of what we have today in a mobile phone, in a smartwatch, or a washing machine. All of these systems have significantly higher computational power. And the reason why this was possible is mostly that transistors were invented. They replaced the vacuum tubes, and after they were invented, they started to shrink in size. The industry has learned how to make them smaller and smaller, from a few millimeters or centimeters in the 1940s down to the nanometer range today. And overall, the size has decreased exponentially at an astonishing rate. Today, their linear dimensions are about 6 orders of magnitude smaller than when the first transistor was designed. That means, of course, the number of transistors that you can put on a chip has increased by 12 orders of magnitude. What is perhaps even more astonishing, but less known, is that also the energy consumption changed dramatically and decreased over the years. You see here the energy consumption of logical circuits between the 1940s and the 1990s. It again decreased exponentially, or the efficiency increased exponentially to an even larger extent. If you compare this, you see that between today and the 1940s, the energy efficiency has increased by about 18 orders of magnitude. Probably it's difficult to compare that to something, but this is definitely an impressive number. And to make it even more impressive, I would like to make a comparison here. Let's assume we have a personal computer, which today maybe consumes 100 watts. And if the energy efficiency were that of the 1940s, it would actually consume 10 to the 20 watts, or 10 to the 11 gigawatts. In case these are not familiar numbers for you, let me clarify that a little bit. 1 gigawatt corresponds roughly to a nuclear power station. So to provide that amount of electrical power, you would have to cover the surface of the Earth, including the oceans, by nuclear power stations at a distance of 25 meters between each other. So obviously, this is not what you want to do, and it means that we have to keep improving the energy efficiency if we want to get more powerful systems. And this has happened again. This is essentially the continuation of the last plot I showed you. Between 1995 and 2015, it has still decreased, the energy consumption has still decreased exponentially. However, this plot also shows you a problem. The lower end of the scale, which is 1, is in units of K Boltzmann times the temperature. And for very fundamental physical reasons, essentially quantum mechanics, it's not possible for a classical computer to go below this. So if you try to improve the energy efficiency, you will hit a major roadblock in the next few years. And this is for two reasons. One is that K Boltzmann times T is the mean energy that every degree of freedom has. That means, for instance, the electrons in a wire. And if this is sufficient to throw a switch, it means that the switches will, in a logical circuit, will become very unstable. It's also the minimum amount of dissipation that you must have in a logic circuit that follows Boolean logic. Boolean logic is not reversible and therefore needs to dissipate energy, create entropy. So this is a major roadblock for classical computers, but if you move to quantum computers, that will no longer be the case because this barrier does not apply to quantum computers. So these are some of the reasons why we believe that there is a major revolution coming up which is often called the second quantum revolution. And physics shows us here what the difficulties are, but it also provides possible ways out how we can overcome these problems. So the first suggestions that we might use something like quantum systems for computation came in 1982. One of the proponents of that idea was Richard Feynman, and at the same time, Benioff made an important contribution. He showed that quantum computers can be universal computational devices. So they can solve any problem which is computable. That did not have direct consequences, but about 10 years later, these three people, Bernstein, Vazirani, and Yao, showed that quantum systems are more powerful than classical computers. Not only they can be universal computers, but they can be more powerful. And that means qualitatively more powerful. And this was a non-constructive proof, so they didn't show an example where it's more powerful, but that came the next year when Coppersmith proposed the quantum Fourier transform, which is exponentially faster than the classical fast Fourier transform. And Shor used that in his factorization algorithm, which made the field very famous. And again, 3 years later came the first experimental implementations of a not yet very powerful, but in principle quantum computer. And that made it popular. For instance, here, this is a headline from USA Today from 1999. It said that the atomic quantum computer will be billion times faster than the Pentium 3, which was then the top of the line microprocessor. Now, this article, which by the way appeared in the section Money, contained a lot of fun but stupid things, like here it says it wouldn't operate on anything so mundane as physical laws. Oops, that sounds very strange for a physicist. How do you build a computer that does not operate according to physical laws? Well, it continues. It would employ quantum mechanics. So quantum mechanics is obviously not physics, in their opinion. Anyway, let's check how this should work in principle. Of course, all these computers are based on digital information. So we encode information in digits and at the basic level in bits. In a classical computer, a bit is a device which can have two distinguishable states to which you assign the numbers 0 and 1. In a quantum computer, again, you have bits and you encode them in quantum states which have to be distinguishable, which means orthogonal. And in quantum mechanics, we have the superposition principle, which says if you can have states psi 0 and psi 1, you can also have the superposition of those, or in other words, an arbitrary linear combination of the two states. And whatever you do with the states psi 0 and psi 1, you can also do with this superposition state. So that's a kind of a Schrödinger cat, but it's normally called then a super qubit, which is abbreviated for quantum bit, and it corresponds to a two-level. So in nature, you have exactly one type of systems, which is a spin 1/2, which has just two levels, two quantum mechanical states. But you can find suitable systems from which you extract two-level systems. And one of the most popular types of qubits are trapped atomic ions. You see them here as these yellow dots between the gray bars, which represent a trap for ions. Now, these qubits, these three ions, encode the quantum information, so you describe them with a quantum state psi. To do computation, you have to apply logical gates, and logical gates are unitary transformations which bring the input state to an output state. Now, the main difference between a classical computer and the quantum computer is that a unitary operation, by definition, is reversible. If a unitary has to have an inverse, so you can do the operation backwards, and that means the entropy is the same in the input state as in the output state, and you have no dissipation. That's why you don't have to worry about the minimum energy that you must dissipate. Now, to create these unitary operations, you need to apply control fields which drive the system from the input state to the output state. And essentially, you need two types of logical gates. One are the so-called single qubit gates, which act on individual qubits. And the simplest one is the same as in the Boolean logic. It's a NOT gate, which brings, for instance, the state 1 to the state 0. And it's its own inverse, so you can also go backward from 0 to 1. In addition to these single qubit gates, you need two qubit gates. And the most popular one of those is the so-called controlled NOT, or C-NOT. It works on two qubits, which have different roles. The first one is called the control qubit, and the control qubit never changes under the action of the C-NOT gate. So the input and the output are the same for the control qubit, but the target bit can be inverted depending on the control qubit. If the control qubit is 0, the target bit does not change, but if the control qubit is 1, then the target qubit is flipped. So you have here the output after applying the control NOT. Now, these are the basic gate operations that you use, for instance, in the network model. So there are different types of quantum computers that you can build. The most popular one is the so-called network model, which is similar to classical computers, where you have a quantum register, which consists of a large number of qubits. And then you have to write your information into those qubits, that's called the initialization step. Very often you just write zeros into that, but it may be that you have to write other information like a number that you want to factorize. And then you apply these unitary gate operations according to the algorithm that you want to run on your quantum computer. And this may be a rather large number of steps that you have to apply, but if it's a suitable algorithm, it will eventually end with the last step here labeled K. And after that last unitary transformation, you have to read out the result, and that means you convert the individual qubits, or at least some of them, into classical information. And the more qubits that you have, the more powerful your quantum computer will be. The individual logical operations act on superposition states, and that's called quantum parallelism. And that's where because all the basis states are operated on simultaneously. And that's where the power of the quantum computer comes from. And there is a nice video here which illustrates that. Let's assume you want to find a path through a maze.
To reach the destination.
In a classical computer, you go to the individual possibilities one by one. That means you will use a lot of time. In the quantum computer, you can search all the possible paths simultaneously.
To each new path.
And so it doesn't matter how many wrong ones there are, how many dead ends. Eventually, one of them ends up at the exit. And at that point, your quantum algorithm finishes and the state collapses to the one that you were searching for.
It's strange, but
that's the basic principle.
When we compare
And
agents, we can see
of the many algorithms which exist, the first ones were implemented on nuclear spin qubits. So this is a molecule called chloroform, which has two nuclear spins, a proton and a carbon-13, and they represent the qubits. So this was the first simple quantum register. And this is a system which is still being used today. It's based on nuclear magnetic resonance, mostly molecules in a liquid. The second type of quantum computer which became available was based on trapped atomic ions. You see here a string of about 30 calcium ions which can serve as a quantum register. And then photons were used. Photons are very nice qubits. They're cheap, they're easy to detect, and they can store quantum information quite well. The main problem that they have is that they don't interact with each other very well. And then there were superconducting qubits, which are very popular today. And there are more like neutral atoms, defects in solids, quantum dots, electrons, molecules, and so on. Now, these superconductors were based on work which was done in the 1970s in Berkeley, and it was awarded the Nobel Prize in Physics in 2025. And some of the people are still very active, particularly in the field of quantum information. Now, the system that I would like to discuss and which I have done most of my work are spins in diamond. They're very nice for academic entertainment because you can work at room temperature, so they're relatively easy to set up, and spins are almost ideal qubits. Now, question is why diamond?
That's quick.
And you see here the advertisement of Marilyn Monroe. So yes, diamonds are a girl's best friend, but you can also enjoy them if you're not a girl. So why diamond? Obviously, diamond is a very valuable material. It's very hard, but it's also pretty boring. I mean, it consists only of a single type of atoms. It's all carbon atoms, and they have a very simple structure. Every carbon atom is surrounded by 4 other carbon atoms. The material has a large band gap of about 5 electron volts, which means it's transparent, so it does not interact with light. So how useful can that be? Well, the main point is that you don't really want to use ideal diamond. What you want is diamonds which have defects. And it's defects which make diamond really valuable. They also give them colors. So you see here some colored diamonds, which are the most valuable ones actually. Anyway, the most popular type of defect, and particularly for quantum information, is the nitrogen vacancy center. Here you remove 2 carbons, you replace one of them by a nitrogen, and you leave the adjacent position empty. That's the vacancy. And together, the nitrogen and the adjacent vacancy make an interesting defect, which you can excite optically with a laser, and it will emit photons. So here you see the photoluminescence spectrum in the visible range. The system has 5 electrons, which together have a spin 1/2. Now, we're not really using this type of defect, but you can add an electron to it, which the defect likes to capture from its environment. So you have 6 electron spins, which together form a spin 1. And you see here in red the corresponding photoluminescence spectrum. There is also a positively charged state, but that's not that useful. So apart from this nitrogen vacancy center, there are other spin centers, like for instance the silicon vacancy in silicon carbide. Silicon carbide is a material which is quite similar to diamond. It has almost the same structure, except that half of the atoms are now silicon rather than carbon. And they alternate between silicon and carbon. But because you have 2 atoms, you have now a much richer structure, and there are actually more than 200 polytypes of this material known. And in these 200 polytypes, you have a vast range of different centers, and it's no matter what you're trying to do with these spin centers, it's almost certain you would find your ideal center within silicon carbide. Particularly, for instance, for some applications, you need optical transition at telecom wavelengths, and that is one of the cases for which it can be useful. Here is the structure of silicon carbide. You see different types of centers like the silicon vacancy, carbon vacancy, the double vacancies, and interstitials. And some of these defects have, well, they have different transition wavelengths, different energy gaps. They all fit into the band gap. Here you see the lower end is the top of the valence band. The upper end of this, which is about 3 electron volts above, is the bottom of the conduction band. And these different states are within the transparent range of the material. So what can you do with these types of defects? You can use them as qubits, or you can use them as sensors. And sensing are actually some of the most popular applications. The reason for that is essentially that they provide you very precise frequency measurement. And frequency measurements are the best way to measure anything. You can, for instance, convert a magnetic field into a frequency shift, as shown here, for an NV center. And so this gives you a sensor which has the size of a single atom and gives you a very precise magnetic field measurement. Or here you can measure temperature change also as a frequency shift. It's a well-calibrated sensor, and you have now a thermometer, again, the size of a single atom. So there are a number of very useful applications for that. How do you operate such a sensor or a qubit? First of all, you have to look at the nitrogen vacancy center. Its electronic structure is that of a triplet state. So you have a triplet A2 in the ground state and a triplet E state about 2 electron volts above. Now, as you know, it's a spin-1 system, but the 3 energy levels are not degenerate in zero magnetic field. There's a zero field splitting of about 3 gigahertz, with the MS equals 0 state being the lowest one. To use that system, you normally excite it with a laser. Say if you use a green laser, which has a photon energy of 2.2 electron volts, you bring it from the ground state to slightly above the excited state, from where it quickly drops down. Now, these transitions are normally spin preserving. In other words, if you start in MS equals 0, you end up in MS equals 0, and you get back to MS equals 0. So nothing exciting happens. Except every now and then, the system crosses from the triplet manifold over to the singlet manifold. There are 2 singlet states between the ground and the excited state, and the system can change, can become a singlet state in a process called intersystem crossing. Now, this intersystem crossing has a higher probability if the center is in the MS equal plus or minus 1 state. Now, if it goes over to the singlet state, it forgets the state in which it was. And so chances are, if you do that multiple times, the system will end up in the MS equals 0 ground state of the triplet subsystem. So if you repeat that, if you shine a laser on it, you will populate mostly the MS equals 0 state. And you can use that, for instance, for initialization of your qubits. You can also use it to measure the state of the qubit, because if you are in the MS equals 0 state, it will essentially just go up and down and emit a fluorescence photon every time. If it crosses over into the singlet fold, which is more probable for the plus and minus 1 states, there is no photon, so you get less fluorescence counts, and therefore the fluorescence can measure the spin state. So this is initialization and measurement, and of course you have to control your qubits. Essentially, you do that by microwave radiation. So here you have again the energy level scheme. The MS equals 0 is the ground state. The plus and minus 1 states are about 2.87 gigahertz above. And if you apply a magnetic field, they will split up. So with a resonant microwave field, you can induce transitions between 2 of these states, and that allows you to define a qubit and to control the qubit. Depending on the parameters of your pulse, like frequency, amplitude, phase, or duration, you can create arbitrary single qubit gates, not only the NOT gate that I mentioned before, but for instance, phase or Hadamard gates. So this gives you full control of the system. Now, so far I've discussed only the electron spin, but of course you need more than 1 qubit, and in particular you have, in addition to the electron, you have nuclear spins. And this is demonstrated here. This is the ESR spectrum, one of the transitions of the electron spin of a single center. As you see, we have multiple resonance lines, and the reason for that is that in addition to the electron, you have also nuclear spins. Diamond consists of carbon, and if the majority of these carbons are carbon 12, which have no nuclear spins and are therefore invisible. But 1% of them in natural abundance are carbon 13s, which have a spin 1/2. And depending on the location, they will split up the resonance line of the electron here, for instance, by 8 megahertz. And then you have a second carbon in this case, which has a hyperfine interaction of 5.8 megahertz. You have, of course, the nitrogen atom, which also has a hyperfine interaction, and it has a spin 1, so it splits it up into 3 transitions. And in this case, we see a resolved interaction with another carbon 13. So together, this is a hybrid quantum register which combines electron spin and a nuclear spin, or multiple nuclear spins. And these types of qubits have very different properties. For instance, the electron spin has a relatively strong interaction. It's essential for initialization and readout, and you can apply relatively fast gate operations. The carbon or the nitrogen 14, they have much weaker interaction, therefore they also have longer dephasing times. In other words, they can store the information for a longer time. And they are present in large numbers, so you can build larger quantum registers with them. And combining the two types is interesting for a number of applications, be it in computation or in sensing. You can, for instance, use the nuclear spin as quantum memory. To control them, you need microwaves for the electron spin, and you need radio frequency pulses for the nuclear spins. So overall, I would say it's clear that you can build quantum computer on the basis of spins, for instance, or on the basis of ions or other types of qubits. So why are we still using classical computers? For instance, I'm using a laptop built on classical electronics for this presentation. There are a number of reasons. One of them is that most tasks for which we use computers today do not need a quantum computer. So if you can do it on a classical computer, you won't want to invest a lot of money to buy a quantum computer. Other issues are scalability. It's still difficult to build large-scale quantum computers, although there has been a lot of progress in the last years in that area. And finally, errors and decoherence. The quantum information is much more fragile. It's more powerful than classical information, but it also is easier to lose. And that means we have to take care of that. Why is it more fragile? First of all, we need these control fields to drive quantum information. And these control fields have a finite precision. And because of the linearity of quantum mechanics, this means that potentially these imperfect control fields create errors. The second reason is that we normally assume we have ideal qubits. Ideal qubits are alone in the universe. They're separated from everything else. And that if that were really the case, they would be quite useless, because if they're isolated, we have no way of initializing them, we have no way of controlling them, and we have no way of reading it out. So they must be coupled to the environment. But this environment is noisy, and the noise tends to degrade the information of the qubit. For instance, that results in the decay of the coherence. So that process is called decoherence, and it causes the qubit to lose its information. So we have to fight these problems, and there are a number of ways you can do that. We can try to optimize the classical apparatus. We can design gate operations such that the errors cancel each other. And we can use quantum error correction scheme. We cannot use classical error correction, but there are quantum error correction schemes. We can also store the information in areas of Hilbert space which are less affected. These are so-called decoherence-free subspaces. And finally, we can actively suppress the effect of noise on the quantum system. So there are a number of ways of things that you can do to get rid of these problems. The bad news is that no single one of these measures will be sufficient. You need to combine all of them to actually make it work. Now I see I probably running out of time, so let me skip a few slides and try to summarize some aspects. So, as I said, we can consider to replace classical computers with quantum computers, but I don't think this is really going to happen. And I gave you the reasons just a minute ago. But you can also ask, will quantum computers ever be useful? And here I'm pretty sure that the answer is yes. And I have a number of arguments. First of all, I would say that even today, quantum computers are useful for quantum simulations. And I would like to give just one brief example, which is about localization. What is localization? If you in basic quantum mechanics, we learn that the ground state of a photon or an electron is smeared out over space. But in reality, in everyday life, we know that most objects are localized, which is very useful. So the question is, where does this difference come from? There is a theory for that, which also got a Nobel Prize some years ago, but it's difficult to actually get specific answers from that theory. And one way around that is to simulate it on classical systems. That's extremely hard. You don't get very far, but there are so-called quantum simulators, which are based on quantum mechanical systems. Here is an example. We start with, so the horizontal axis is time, the vertical axis is space. We start at time 0 with a localized system on 1 qubit, and then we let it evolve under a suitable Hamiltonian. You see it spreads out to become completely smeared out over the available space. Now, this process can be stopped or slowed down if you include a perturbation. So you have, for instance, in a crystal, you have dislocations, and scattering at these dislocations causes the spreading to slow down and the system becomes localized. And you can do that on a quantum simulator much easier than in real life because you can control, for instance, the perturbation strength. And this shows you that the system does have a quantum phase transition for low perturbation strength. You have a delocalized phase for high perturbation strength. You get into a localized phase. So this was done with a large quantum register, which allows you to simulate quantum, but it's not a general purpose quantum computer. So that was my first argument. Quantum computers are already useful today, and we are almost certain that future computers will use quantum effects. I mean, I showed you the issue of energy efficiency, for instance, minimum dissipation, and so on. And there is a third argument, which is based on Krömer's lemma on new technologies, which says that the most important applications of any sufficiently advanced technology are always created by this technology. I guess I have to skip a few more slides, but I would like to show you one possible application, which is about image processing. Of course, we know that today most of the computer power and the information transfer in the system is based on image processing, movies or graphics. And the reason for that is that, well, we communicate more and more with images, but this is a very time-consuming process. It takes a lot of computational power. And it turns out you can replace classical processing for that with quantum processing, and it can save a lot of computation storage effort. So here, for instance, we have a typical task for image processing. And if you have an image, say with 16 megapixels, of course, in a classical computer, you would use for a black and white image 16 megabits. Now, it turns out in a quantum computer, you can store the whole information in 24 qubits. And you can save a lot of storage space, and the computation can be incredibly efficient. Let's assume you want to find the border between black and white area here. And if you do that on a classical computer, you need about 16 million operations. On a quantum computer, you need one operation on a single qubit, independent of the size of your image. So that can be very, very efficient. Let me come to the conclusion. I try to show that quantum technologies offer a lot of options for increasing the efficiency of many processes. There are a number of different technologies like quantum communication, quantum sensing, and quantum computing. And I would like to thank you for your attention.
Thank you, Professor Suter, for your wonderful presentation. If there are any questions, so we have a couple of minutes available. Any questions? Online? We watch.
Sir, may I audible?
Yes, well,
Sir, thank you very much, first of all, for the very detailed presentation and about depth of the quantum. I have a simple question. I have seen various algorithm of quantums. Although in encryption, decryption, it's doing a wonderful job. But for term of classification or deduction, where the pattern we have to identify, still we need hybrid quantum. Why quantum is not at this stage is capable to identify or differentiate between pattern independently, sir?
Between what? Can you repeat the question?
Sir, I will repeat my question. Why quantum at this stage is unable to identify, differentiate? For example, like we have algorithm like XGBoost or some other neural networks. So we use quantum computing to identify or separate these classification problem like cancer detections or sort of climate weather or like that. But what I have seen that quantum at this stage till today independently is unable to find 100% pattern what we need it. What is the reason? Means still, I think it is immature stage at this stage till today. We need more algorithm.
Well, I think algorithms are around. The main problem is that the currently available machines are not as powerful as we would like them to be for some applications. For instance, it has been proposed that for implementing Shor's algorithm, you may need several million qubits, but today's computers only have a few hundred qubits that you can control sufficiently well. And the second reason is that what I mentioned, that the information is lost too quickly. So we have to learn how to be able to preserve the information long enough so that you can run the algorithm for a sufficiently long time. And the current projections are that a really useful general purpose quantum computer might become available in 5 to 10 years.
Okay, I have a question. So you're talking about transistor that it can be miniaturized to a very small size. So in terms of quantum computers, superconducting qubits have potential to be miniaturized. But can you comment about neutral atom quantum computers, ion trapped ion systems, and maybe diamond vacancy centers? How do they compare?
Yes, I would say in terms of miniaturization, the solid state systems are potentially the best because you can have the say the diamond and V centers, in principle, you can have with a spacing of a few nanometers or 1 nanometer. For the ions and neutral atoms, the spacing is more in the micrometer range. But this is given by the wavelength of the light that you use to control them. So which means in volume, of course, it's 9 orders of magnitude larger, but I don't think that is really critical. It's more, I mean, even if you need a million qubits, it still fits into a relatively small size. But there are definitely issues, for instance, in terms of power consumption or the current version of the superconducting qubits, as well as ions, they have to be operated in very low temperature in the millikelvin range. So you need a cryostat, and the whole thing has to fit into that cryostat. Now, for the superconducting systems, currently you need for every qubit maybe 10 control lines which connect the qubit to the outside. You cannot imagine that you have a million qubits, each of them 10 control lines going to room temperature. Now, one way of solving that now is in the last few months, several groups have managed to build control electronics, so-called cryo-CMOS, which can operate at millikelvin temperature. Of course, conventional electronics cannot operate at millikelvin temperature, but you can adjust it, and if that can be done sufficiently well, then at least you can do the whole operation at low temperature, and that will solve some of the scaling problems.
Thank you very much, Professor Dr. Sutter. It was wonderful presentation. Your audience is really mesmerized.
Thank you.
Thank you. So thanks again. Take care. Bye.
Bye-bye.
I'm going to present my work on quantum supremacy is defined. Here I'm going to present the basics, which makes us understand how quantum computers are useful in our conventional classical computers in how many ways. So when we think of the classical computers, the first version of the classical computer was named as ENIAC, and it was presented in 1945. And it was just presented in previous presentation. It was a huge, big device, and but it was able to add and spread to only 2 digits. Today, we have the first generation of the quantum computers. And this is, again, at present, a big device, and it is having 160 qubits at maximum when we talk in terms of the punchable atom-based quantum computers. So it's the technology is improving very much, and the better and better devices are coming very fast. So as Professor Sutter was mentioning, that in next 4 to 5 years, maybe we have office quantum computers as well. So in our daily life we may use. So when we want to start talking about computing, we start coming towards the numbers. In our conventional use, we use the decimal units, and we write everything raised to the 10. But for computers, we use binary units, and then and there we write all in 1 and zeros. For example, a number 11 can be written in this form, just down here, and we can see that it can be expressed in a simple 1, 0, 1, 1 way. And now, in this way, we are in a position to write all the decimal numbers in binary form. This helps us to pick up a mechanism for our computers and invent a bit. And bit can be named as a on and off scenario in a conventional requirement for a computer. If a passage of electron from transistor can be named as 1, or a rocket of an electron can be named 0. Or in some other scenario, the charge capacitor can be named as 1, or in the absence of charge, it could be named 0. So a classical system can be considered in this way 1 and 0, which is used in our computer. In contrast, in the quantum mechanical way, we have any two-stage quantum system as a good candidate for a qubit. It's a prototype of a conventional bit. So any two-stage system can be considered as a qubit. And many examples such as two-level atoms. So we consider the ground state at 0, high state as 1, or it can be spin of an electron, spin up can be named as 1, for example, spin down can be named 0. And then we have polarization of a photon or angular momentum state, again, making a qubit in this way.
qubit is having advantage of being written as a superposition of 0 and 1 because the non-locality of the quantum mechanics permits us to write both states simultaneously, and this gives us a superposition. Superposition is only requiring that the coefficients alpha 0 and alpha 1 should be having a special relationship, and that is alpha 0 mod square plus alpha 1 mod square should be equal to 1. And the mod square value is named as the probability. So that simply implies the probability of finding 0 and probability of finding 1 when summed up together should be equal to 1. So if we talk about an electron in lower state as 1 and excited state 0, excited state, lower state as 1, excited state 0. So that can be considered in the form of a probabilistic value. So if it is only ground state, so we say the probability is 1 there, and thus the next probability is 0, and so on. But it is also sometimes considered in the form of coining a coin. When you flip a coin, it is in the air, and then you say that what is the probability of finding head or tail. So this is a conventional way of presenting the concept of probability and connecting with the qubits. But if we see very carefully, this is not complete picture of a qubit. And the simple reason is because these probability amplitudes are complex numbers. And again, this is special characteristics of the quantum mechanical systems. And this makes us to say that whenever we talk about the amplitude, we have to have the corresponding phase as well. And the phase is important. Still, it is keeping the requirement maintained, that is alpha 0 mod square plus alpha 1 mod square should be equal to 1. So phase is very important. Phase is very important, and if we take one phase out, so we get a relative phase phi, and that is very helpful defining a relative phase between 0 and 1. This phase is very important in various different applications in quantum computers and in quantum information. For example, when we talk about quantum search algorithms, so flipping of a simple phase value will give us a possibility of completing our search. So that's a very interesting thing. So that is also named sometimes as the Grover's algorithm. So that is all based on the change flip of the phase is sufficient. So phase information cannot be ignored while we talk about quantum mechanical qubits. It's very useful in various ways. And again, the presence of this phase up there makes our qubit available on any point on this subfield, which is sometimes named as block subfield. So alpha 0 plus alpha 1 mod alpha 0 mod square plus alpha 1 mod square simply describes the radius of this subfield, and then the value theta and phi they bring us anywhere on the surface of the sphere. So any point on the sphere would be named as a qubit. So if we ignore the phase concept, we are on a circle, and if we ignore the probabilistic nature, we are talking about the classical bit. So we are only talking about the 0 and 1, which are the pole, the 2 points on the pole of these subhere. So that means the quantum mechanical setup is larger than conventional classical and even the statistical information as well. So phase is important in that sense. Another very important thing is that, again, starting from the concept of qubit, which is in the form of superposition, we enter into 2 qubit scenario. So this is simply, we have qubit 1 and qubit 2 together. And once we open this system, once we multiply them together, we have 4 terms available to us: 0, 0, 0, 1, 1, 0, and 1, 1. Now, a classical system with 2 qubits may have these 2 possibilities all the time. The two bits with us may have value 0, 0, or it may have 1, 0, or it may have 0, 1, or 1, 1. But the interesting thing is that if you want to have all these 4 combinations together, you require 8 bits. And here we are doing the same, all four combination 0, 0, 1, 0, 0, 1, and 1, 1 just by using two qubits. So because the value alpha 0, 0, alpha 0, 1, alpha 1, 0, alpha 1, 1 would be now defining the corresponding probability, which is controllable probability. So that means that what we have in our conventional classical system with the help of 8 qubits is available to us in a quantum mechanical domain just by 2 qubits. If we generalize this discussion, it becomes more and more interesting, because if we have 4 qubit scenario, so this is the same thing written for our quantum system in a matrix form. So if we have 4 bits with us, we can write these 4 bits in 16 different combinations. Now, if you want all these 16 combinations at the same time together with us, we require 16 multiplied by 4 bits. And that's a big amount of bits, but the same, all 16 combinations are with us once we have only 4 qubits. So this is something very interesting. This gives us a possibility of generalizing our understanding. And that means that if we want to have 1 kilobyte, we require 2 raised to the power 10 different we have 2 raised to the power 10 combinations with us in 1024 bytes, and only 10 atoms are sufficient to write all these 1024 bytes data. And if we have 1 megabyte, which is 1024 kilobytes, so we require 2 raised to the power 20 combination. We have these 2 raised to the power 20 combinations, and we require only 20 atoms, that is 20 qubits, to write all this data on these systems. Keep going, and then we see that if we want to have 1 petabyte, which is 1024 terabyte information, we require 2 raised to the power 50 combination. We can make 2 raised to the power 50 combination. There is some glitch. It's classical computer. Okay. Okay, so here we go. So here we say that if we have 1 petabyte, which would be 1024 terabyte data, amount of data, so it would be written only on 50 qubits. So to write all this, and this, interestingly, this amount of data can be compared with any, with all data available on internet in any language. That would be something like 1024 terabytes data. So we require only 50 qubits to write all this data in a quantum computer, and just keep going. So at present, in our conventional use, we have a quantum computer up to from 50 to 100 qubits. So this is named as noisy intermediate scale quantum computers. So that's why this field is very interesting with these with these so many qubits. When we want to come to the processing of data, so again, something very interesting in comparison to the classical computers, because in classical computer, we use logic gates. We want to perform some processing of data, we use logic gates. We have NOT gate, which changes 0 to 1 and 1 to 0. And then this is the only single bit gate in classical domain. In quantum mechanical domain, we have, beg pardon, in classical domain, for 2 bits, we have AND gate, OR gate, XOR gate, and so when we want to perform anything on 2 bits simultaneously, so we perform the processing with the help of these AND, OR, or XOR gates. So now, interestingly, when we enter into the quantum mechanical domain, we again have, this again classical logic gates. So classical logic gate would be a NOT gate changing 0 to 1, 1 to 0. It's another way of presenting it. And it would be two input and one output gate. And once we look at our logic gates in this way, we see that this way of writing the processor has lost already one bit information, because and 2 bits information was consumed in a logic gate, and 1 bit information is coming out. So information is lost, and that lost information is also coming to the loss of energy and restricting reversibility. We don't have any reversible scenario in this situation. But if we enter into the quantum mechanical domain, so now the quantum mechanical system can be considered as based on single bit logic gates and two qubit logic gates. So single bit logic gate is going to do the same. If it is our qubit is in 0, it will change to 1. If it is in 1, it will change to 0. And there are other logic gates other than the NOT gate, other than the NOT gate only. We have phase gate, which generates phase on a qubit, and we have Hadamard gate, which generates superposition on a qubit. So if we want to have two qubit logic gates, we have popular example as a control NOT gate, because our input is 2 qubit, and our target, our output is again 2 qubit. So how it works that if we have Q1 and Q2 as the input of qubits, the control NOT gate works on this. It does not change the Q1, the first qubit, but it changes the second qubit conditionally depending upon the value of the first qubit. So this way we obtain 0, 0 as 0, 0, 0, 1 as 0, 1. So 1, 0 as 1, 1, 1, 1 as 1, 0. So this is interestingly in quantum mechanical domain, we have 2 qubit input and 2 qubit output. So here we have not lost a qubit, and that is saving us from anything like energy loss. And we have reversibility ensured as well in this scenario. So this is quite an interesting domain. And again, there is no information loss, no heating effect in a sense. So this helps in understanding the quantum mechanical equations very much. All these effects in the classical circuitry as well. Whenever we make circuitry, we are very much deterministic. We know a given input will be processed, and we shall come up with a definite answer as an outcome. But in the quantum mechanical domain, we see that a given input is being processed by some processor, which is quantum mechanical, and we don't lose any information. So the input is almost the same as the output, and we don't have any information loss. This ensures the quantum parallelism and at the same time the reversibility. And this generates many interesting effects in quantum computing and quantum information, because which are not seen in the conventional computers or computing setups. For example, if we have a copying setup, copying device, it would not be possible to perform a quantum copying from a circuit. It will be the outcome would be in an entangled state in some scenarios. So okay, let's read to the next slide. And okay, now when we talk about the classical computing and we enter into the discussion of quantum computing, we have classical bits, whereas in the quantum domain we have the quantum mechanical bits, or named as qubits. We have classical logic gates, which are 2 input, 1 output gates, and whereas in the quantum mechanical domain we have quantum mechanical logic gates, which are 2 input and 2 output gates. They are also expressed by unitary transformations, because unitary transformations also ensuring the reversibility. And then we have classical circuits, which are now replaced by the quantum circuits, where we have parallelism available and reversibility available. And in the classical systems, we have reading, we read the output, whereas here we measure the outcome which we want to have. So in quantum mechanical computing, our discussion starts with initializing our qubits, and then we run our circuit and measure our final outcome. The important question up here comes that how we can really build these computers. And the second important question comes that in how many ways we can operate these computers. So while we talk about the operating computers, we enter into the discussion of algorithms. And there we have various different kinds of algorithms which have definite advantages on our conventional classical domain. Otherwise, there is no fun of using any quantum mechanical circuit or quantum mechanical algorithm. So in quantum algorithms, we have popular one, which are Deutsch algorithm. We have Grover's algorithm, Shor algorithm, and Quava, and then Falcon available to us. And when we want to talk about quantum algorithms, we want to first be ensured that we are getting some advantage. There is some inherent advantage in quantum computer which we can't get in our conventional classical domain. So we pick up a simple example here, Wilmets only, and that is coming from the Deutsch algorithm. So this is an algorithm which is sometimes is also named as a decision making or Entscheidung algorithm. So this is decision making in a way that if you want to decide between a balance function or a constant function. So how many observations we have to make? For example, a balance function can be named as that if we give one value, the outcome is a value. And if we give another input value, the outcome is another value. So this is defined in the upper line. And the constant function is that whatever input we give, the answer is the same. You can compare it or you can connect it with some physical examples, for example, such as like a coin. We want to think here that a coin is a fair coin or a unfair coin. If a coin is fair coin, that means it's on one side it is having head, the other side it has a tail. If an unfair coin would meaning on both sides it has heads, or on both sides it has tails. Now, if you want to make this understanding, the coin is fair or unfair, we have to simply do two operations. We have to read it from the front and then turn it on the other side and read it on the other side. It's the simplest task we can perform. Now, it would be wonderful that if we perform all this work quantum mechanically, and just by one side, just by one observation, we can tell it's fair coin or it's a unfair coin. And that's a quantum advantage. That gives us an understanding that we are really doing something meaningful. Because we are not to do the measurement twice. So this is the simplest algorithm in that sense. So if we have defined our coin in the form of function, that function, constant function means an unfair coin. That we on both sides, the answer is that we have heads, or on both sides we have tails. So that may be connected as constant function. A fair coin can be considered as a balance function. So if we write corresponding quantum circuit, we apply Hadamard gates, we apply the we apply the unity operations and read the final output. So what we achieve, our initial state is 0, 1. The 2 qubits we are entering is we are providing as input data is 0 and 1. And the first 2 Hadamard gates develop the superpositions. So we get after the first step, we obtain this 0 plus 1 and 0 minus 1 scenario, because this is the operation of Hadamard operation. It changes 0 to 0 plus 1, it changes 1 to 0 minus 1. So it's a simple state obtained after the first operations. And then we apply the processor. The processor has the information of the function. it's a constant function or the variance function. So if the function is a constant function, so we obtain the state after the processor again as this two separate superposition states, but 0 plus 1 and 0 plus 1 sitting here, 0 minus 1 sitting here. But if the function is a balance function, so what we see, the outcome is changed. It is 0 minus 1 and 0 minus 1 on the two things. And here we just apply one Hadamard again. What it does, that it will make, in case of constant function, it will make the qubit number 1 as 0, whereas in the balance scenario, it will make the qubit number 1 as 1. So now just by looking at the first qubit, we are in a position and make the measurement on the first qubit. If it is 0, the first qubit is 0, we say that the function is a constant function. And if the first qubit is 1, we say the function is a balanced function. And very interestingly, the sign value plus and minus tells us what is the result. Once it is balanced, making f0 is 1, f1 is 1, or f0 is 1, f1 is 0. That is interchanging the value. And the same plus and minus will change if in a constant function f0 is equal to f1 is equal to 0, it will plus sign, and f0 is equal to f1 equal to 1, it will make minus sign. So a simple experiment observation will tell us it's a valence function or a constant function, or a fair point or an unfair point. So we can associate with that. So there are other interesting algorithms which we can talk in later in the next phase, and there's this Shor algorithm, and it performs the factorization. The Shor algorithm is the factorization is very important, as it was discussed in the first presentation today, that it is used to perform the cryptography, classical cryptography breakable. So if it is possible that we are in a position to factorize large numbers, we are very good in performing breaking the conventional cryptographic codes. So all work around quantum cryptography. All work behind the Shor algorithm is that how we can factorize large numbers. Just concluding, not taking much time, that if we compare it with the estimation of time and we connect it with the digits at hand whom we want to factorize, we see in the classical domain the time increases very fast. But in the quantum mechanical domain, it's very interesting to see very large numbers can be factorized in very efficiently. For example, if we have on the vertical axis as nanosecond, so this operation can be performed in few seconds in a quantum computer, factorization of a 100-digit number, 1,000-digit number. But the same work would be taking the life of a universe to factorize that big number. So it's a big advantage in that sense. So here I conclude my discussion, and thank you.
मैंने लैपटॉप कनेक्ट यूएसबी से तो ये कंपाइलर है, ये तो फोन नहीं करता, ये सेटअप इंस्टॉल हुआ है Zoom इसके ऊपर है मैंने So we'd like to thank Dr. Khan for the good presentation. We're gonna be starting with the demo. I'm gonna introduce myself for a bit, and then we're gonna start with this setup that how you can initialize QSkit and work in quantum circuits. And then we're gonna see some poly-X gears applied to some qubits and how we can view the state on block sphere. And then I'm gonna be explaining a little code, how to make a function and also QSkit, where you can run your quantum circuits on quantum simulators. But you can also get a quantum API key from IBM, which would be helpful if you want to run your simulations on a real quantum computer device, right? So for this,
the dot plus के साथ में इसको वो जरा बड़ा कर
what is it?
zoom करें
Is it better?
yes
Okay. So the first thing is basically I want to ask from the audience how much, like how many people are a little bit familiar with the QSkit and they're able to execute a program. Okay, then that would be good that we were gonna start with the basics. Okay. So I would be explaining what is QSkit and what is this environment, what is Anaconda, and what is Jupyter Notebook. And then we're gonna see a demo in 8 to 10 minutes in which a person from IBM is gonna explain that how can you download it and get started working with the quantum circuits. So what is QSkit? So I would say that QSkit is an IBM open source quantum development kit that can be used for quantum computing. We can use Python and Anaconda for simulation and to create and simulate quantum circuits. Now, going forward, what is Jupyter Notebook and what is Anaconda? That's an important question. So Anaconda can be considered as a toolbox that contains all the tools. So it's basically a Gaussian distribution designed for data science, for machine learning, and for scientific computing. And as long as we want to know about the Jupyter Notebook is basically an interactive environment where you can write your code in the blocks and then simulate blocks and see your results. So I'm going to be shifting. I'm going to shifting towards a little demo of how you can install the QSkit and start working, because I have already installed QSkit and Anaconda in my laptop. But this is a simple 2 to 3 minutes of a guy explaining that you can install Anaconda, and that has also like predefined Python distribution libraries. And then you just start the online server of Anaconda. So
if you're new to the series, we cover topics in quantum algorithms each week, so be sure to like and subscribe. Today, we're going to be learning how to install Qiskit and use a very specific circuit level to build our first quantum algorithm. In order to access this library, we're going to have to install Qiskit locally first. So let's go through really quickly how to do this. So Qiskit is an open source SDK used to programming quantum computers using Python. And don't worry if your Python skills aren't there yet, we'll work through things slowly. So the first thing I'm going to do is navigate to qiskit.org. This will tell me exactly how to install Qiskit on my machine. And there's generally two options for running Qiskit. You can either run it on IBM's hosted Jupyter notebooks, or you can install it locally. And the first thing I want to do is, if I don't have Python installed yet, is to just install Anaconda, and this will install all the things I need for Python. Click download. I have a Mac, so I'll just do the 64-bit graphical installer and download it. And like always, if you have Windows or Linux, just choose the appropriate downloader. Okay, so now that Anaconda has downloaded, I'll just open this up. And I'll install. So what I'm going to do first is set up my Python environment, which is a good way for me to organize my Python packages so that I have all the correct versions of all the packages in one place. So what I'll do is conda create dash n name of my environment, which will be coding with Qiskit or and n thing. Hey, if you scroll down slightly further. Series, we cover topics in quantum algebra. Install a Qiskit and use a very specific circuit library in order to build your first quantum algorithm. In order to access this library, we're going to have to install Qiskit locally first. So let's go through really quickly how to do this. So Qiskit is an open source SDK used for programming quantum computers using Python. And don't worry if your Python skills aren't there yet, we'll work with things slowly. So the first thing, I have a Mac and I'll install packages in one place. So what I'll do is conda create little. I'm going to choose the Qiskit stable installation algorithm.
All right. So I will briefly explain that what he did is basically he installed the Anaconda environment that comes with a Python, predefined Python libraries. And then he installed from that Anaconda environment pip install Qiskit. Qiskit is a library, as I explained, that is used for quantum circuits and all. And then he started working. So I'm gonna explain this now with my laptop that I have created some demos for today. But I would be happy if you have this environment on your laptop and then we can go along, because in the coming days, we're gonna be doing teleportation and super dense coding, circuit diagrams or programs. So it would be good if you can simulate with me. But for today, I would be explaining that we have initialized setup, and we're going to start with the first block, and I'm going to explain every line in the block and what is happening and how can we make like a little circuit and a little quantum circuit and simulate it. All right, from the starters. Now we have Qiskit installed. What you have to do is you have to go to the Anaconda prompt and you have to write a Jupyter notebook. And after writing Jupyter notebook, you will get an online server where you can write your codes and save it. Okay. So the first block I'm going to explain. So first you see that from Qiskit, you're importing quantum circuit, assemble, and air. So I would briefly explain these three things that we are importing. The first thing is quantum circuit. So quantum circuit is used to create quantum circuits that is very straightforward from the name. The second class that we are exporting from the library of Qiskit is basically assemble. So assemble is a class that converts our quantum circuit in an executable format that quantum simulators take. Now, air is basically the Qiskit simulator, which is called backend simulators, in which we're going to have some counts and shots, and we're going to give our qubits and gates, and it's going to simulate it and give our output back. For the second line, we're importing some constants by square root, and from the Qiskit visualization library, we're exporting block multivector and plot histogram. So block multivector is basically to see your states on the block sphere as explained by Sir Farhan, and his histogram is basically to see how the probabilities graphically. And now the third line, that is SEM is equal to air.get.backend air simulator. It's basically we are explaining here that we are going to use this machine that would be there for simulating things. So air is the air is basically a class that have air backend simulator. Right now we're gonna execute this and we're gonna go to the next block. So the first block is here is basically how we can use a quantum circuit, how we can initialize the quantum circuit with how much bits we want to take, and how we can use a poly X gate. So I'm using X gate on qubit 0. So the first line is basically QC is equal to quantum circuit 1. Here we are telling our machine that we are having a circuit with the 1 qubit, right? So in our program or in Jupyter Notebook or in Qiskit, we start with the predefined state of 0. If we want to start with the 1, then we have to explain our machine that you have to start with the initial state of 1. But right now we are starting with the 0. So next I'm basically applying, which is the second line where I'm applying a NOT gate on our qubit. And I really want to see that what is happening when I'm applying a NOT gate. So QC.draw is a function that would give you a circuit that you have a 1 qubit, and then we are applying an poly-X gate, or in classical we call it a NOT gate. As explained by Sir Farhan, that when a poly-X gate is applied on a qubit 0, it converts into the 1, and if it applies on a 1, it converts into 0. Now we want to test it, that if our poly-X gate is working fine, and we want to see in a block sphere that what is happening with this functionality or with this gate, right? So let's see the result. So there is a certain format with how we can see the results, because in quantum computers we have to have a certain executable format which we can give to the air backend simulator, and we can see on the block sphere that what is happening. So first thing is basically we have to save the state vector. That is important because the state vectors are used for visualizations. The next thing is basically using the assemble. So this is the class that I explained in the first block, is basically there to convert to make a executable format to give it to the air backend simulator. This line I'm going to break down in the 3 parts. So we have a state, and we are running that object in a simulator. We are getting back our result, and then we are like retrieving the quantum data that gets state vector, right? So first we're going to save the state vector, then we're going to call the class assemble that would convert our quantum circuits into proper format. And the next thing would be we're going to simulate it and retrieve the result. The last step is basically I want to see in a block sphere that what is happened to state after it has passed from poly-X gate. So as most of the people know by now, that poly-X gates would convert the 0 bit into the 1 state. So you can see that we started with the qubit 0, and now we're in the state 1 on block sphere. Right? So this is a simple demo of a program that how can you use a single like poly-X, poly-Y gates, but it's a starting, because in this Jupyter Notebook and in this QSkit open environment, you can use many other quantum algorithms, for instance, teleportation, Tor algorithm, and many more, right? Next, let's go to the next block. And for my curiosity, I wanted to show that we can also apply the Y gate, the poly-Y gate, poly-Z gate, and we can draw the circuit to see that what is happening that we're doing it. So we have an X gate and Y gate and Z gate. You can set the initial state to 1 or 0. Then you can simulate using these predefined set of instructions that are necessary to simulate in the quantum simulators. And then you can see your results. We're going to get a little bit complicated for the next block. And
Can you zoom in a little bit?
Oh, okay. Just let me know when it's visible.
So
Is it?
Is it visible?
Is it visible? But you're going to get this code as well, because I want you guys to simulate over the Jupyter Notebook as well.
Can you face the audience? Like, can you move the chair?
Yeah.
Okay.
All right. So the next thing that's important is basically we are creating an X measurement function. I explained this, that when you have when you initialize a qubit in a quantum circuit, you start with the state 0. In QSkit, the libraries start with the X basis. No, sorry, Z basis. That is 0 and 1. But what if we want to start with the X basis, that is plus and minus? For those of you that don't know that what are the bases are, in analogy, if we want to explain it, that if you want to explain the position of a particle in a room, you would need a reference for it, right? X dimension, Y dimension, and you can pinpoint it, that where is it. Similarly, in quantum domain, we have bases. First basis are first. So first bases are 0 and 1. We are predefined bases in which QSkit works. But if we want to start with the plus and minus bases, we're gonna make a function about it, and we're gonna see what happens if we do that. And I hope you guys are curious to see that what is gonna happen if we're gonna apply a Hadamard gate, which is a gate that produces a superposition in equal probability on a plus or minus basis, right? So the first thing, I'm defining a function with the parameters. I'm defining a classical bit, that is C bit, and we have a quantum bit, and then we're defining a quantum circuit. Now we are applying a Hadamard gate that is QC. Is it visible? Is it visible now?
Yes.
Not really. Now, all right. So the second part of the function is we're applying the Hadamard gate on a qubit. Right now, we're not defining the qubit state to be 0 and 1. We're defining a function for general parameters where we have a qubit. And later on, we're going to send the values of the qubit to a certain function. So I don't know if the people are a little bit familiar with the programming. In programming, we do that. We define a function if we have to use it for the general purpose in our program multiple times, right? So the second thing is we're going to measure the quantum bit and save the result in a classical bit that we have defined. And then we're going to return the quantum circuit. Now this is the function that we have defined, and now we're going to pass on the parameters we want to. All right, so this is where we have defined a function, and now we want to see that if you want to pass on parameters and see that what happens if we start with not with initial state of 0 qubit, rather with a basis state of 0 plus 1, 0 minus 1 divided by under root 2. See, so if we apply Hadamard gate on that basis, what is gonna happen? So now when we have defined the function, then we have initial state where we're giving probability amplitudes to alpha and beta. As you guys already know, we can define a quantum state that Sir Farhan explained. That would be alpha 0 plus beta 1. So alpha would be the probability of the 0 state, and the beta would be probability of the 1 state. And now we have to define some values for alpha and beta. So here I'm giving alpha as 1 by square root 2 and beta as minus 1 by square root 2. So we have initialized our probability amplitude of the state. The second thing is basically we are defining the quantum circuit with the 1 qubit and 1 classical bit. So that 1 is defining that you have 1 qubit and 1 classical bit. And the next part is basically I want to start my initial state not with the 0 as we did above when we say that we have x0 quantum circuit 1, we have a state 0. But now we have to change our initial state. So what we are doing, we have initial state probability amplitude state save in that variable which is initial state, and we are applying that to 0 qubit. So what is it making? Is basically making our state is equal to 1 by square root 2 0 minus 1 by square root 2 1. Now this is the state that we are giving to our quantum circuit, and what it would be do. This is the qubit. It would it would go on to the function and it would apply a Hadamard gate on that state, not on 1 now, but we have initialized the state in the superposition state, which is called a minus basis or plus basis. We use it, right? And the next part is we're going to measure the qubit and save our values to classical register. And we want to see, draw the whole circuit and what is happening in the circuit. So you can see the circuit diagram is basically we have initialized our probability amplitudes, we're applying the Hadamard gate, and then we're applying a measurement operator. And that while is explained that we're saving this state into the classical register, right? That is C1 that we have defined. So out of curiosity, can anybody care to guess that what is going to happen if we apply a Hadamard gate on minus basis? What do you think? We will get 0 or 1?
And then we can still write the minus basis into the
exactly. So it's basically a reference, a relevant thing. But if we apply Hadamard gate over 0 minus 1 divided by under root 2. So what is going to happen? I'm going to just do a little visualization of the exact procedure that is happening, but we're going to simulate it later. So that Hadamard gate would apply on 0. It would give it 0 plus 1 divided by under root 2. Then it would be applied on 1. That would give 0 minus 1 under root 2. And after a certain manipulation, we're going to see that we have 1 basis left, right? So the second thing is basically, again, if we want to simulate our quantum circuits, we have to go with a certain format. We have to define an object. We have to call the assemble class. And then we're going to also give a quantum machine the number of counts, right? So this is a concept that I also want to explain here, that what is shorts. We always hear that there are shorts and number of counts. that we do for the quantum machine or quantum circuit or quantum simulators. So if we execute a circuit for the one time, we call it a one shot. But since this is a different from classical computers, in classical computers we have input and output. It has one input, one output. That's okay. But in quantum computers, we have one input, but we have results in probabilities, right? So the more shots or the more counts we're going to give, the more time we're going to execute that quantum circuits, and the probability would be better. So quantum simulator decide in a way that it is closer to 1 or it is closer to 0. The more times you're going to simulate, the more accuracy. It's just like quantum machine learning. If you want your machine learning algorithms to be accurate, you have to give more data, right? In order to get that accuracy. So now here I've defined the counts, and I'm going to get the counts, but the maximum counts Qiskit offers 1024 counts. And then I'm going to plot the probability of that counts. That counts is basically going to give us the execution parameter of the circuit that we have described. So if we do that, then I get this histogram probabilities that we have 1, right? So by applying the Hadamard gate on minus basis, you can change this initial state. That would be a good exercise for you guys to do. You can change this initial probability amplitudes, and you can apply a Hadamard gate, and you can see how this is happening in your simulation, right? You can change the initial state to anything you want. So after that, we see that our states collapse to the 1. So we are applying the Hadamard gate, and we are converting into different bases. So this function is basically elaborating that we have different bases in which we can work with the quantum computers. All right, fair enough. Any questions till now? Okay, let's move forward. So I would like to say that it looks a little bit kind of thing that it's very hard to understand, but in reality it's very simple. We're just trying to understand how can we have a simple building element of the quantum computers that are quantum gates in our program, and we can use gates to make a very detailed algorithm. For instance, in teleportation algorithm, we are using Hadamard gate and control not gate. That is basically the whole teleportation protocol. And in the next section, I would also simulate teleportation circuit and see what is happening if we are transferring one state of Alice to Bob in reality or not, right? So another demo that I made for today is basically unitary gate transformation. So again, for practice, you have to define your quantum circuits with however qubits you want to use. If you write 1, then it will give you 1 qubit. You can write 2 and many others. Given that we have some threshold using in the simulators or Qiskit. Now I'm using a U gate. The parameters I'm giving in a U gate is pi by 2, 0, pi, and 0. So don't get scared by this command. I have written a comment that this is basically theta, pi, lambda, and qubit. So these are phase parameters and all parameters that are used in unitary gates. And then we are applying this on qubit. Again, we want to draw this because why not, to see that what is happening. So if we draw this, you would see that we have U gate with pi by 2, 0, and pi. These are the parameters. Now, I don't know if I give this parameters, what's going to happen to our qubit. And again, this qubit is going to start with the initial state of 0 because in our Qiskit, our state is predefined to start with the 0 state, right? If you want to change it to 1, we have to give it an initial state that I did in the initialization, that please start with a 1, not 0, right? So I don't know what this function is going to do, but we're going to find out together. So again, we have to save this state vector for the visualization. Then we have to call the class assemble to convert our whole circuit into executable format. And then we're going to run the state and get the state vector. Again, you can see your state vectors on histogram. Also, if you like to see your state vectors on a block sphere, the both are available, however you like to do it. So this state I'm going to see on the block sphere that what is happening to get insights of what is really happening with the state that we have given, right? So after giving this parameters to unitary gate and by simulating on a quantum simulator that is given by IBM, we got to see that we have an X state. So X state is basically a plus state, which is 0 plus 1 divided by under root 2. So we have created a superposition state in this regard. So this concludes my first demo for today. We have learned, and I would really like request you guys to go today and install this And the next time tomorrow when we're doing a simulation or we're having this demo, we're gonna do it together. So we can have that at this whole teleportation protocol, and we can see if we apply Hadamard gate. Tomorrow we're gonna see if we apply Hadamard gate. We're gonna see the equal probability of 0 state and 1 state, right? So this was the, I'm gonna forward the link for the YouTube video that explains the initialization. And I'm also gonna send this code to everyone. So tomorrow you have this code predefined in your laptop and you can simulate, right? So this was the demo to explain that really you can simulate and have quantum circuits and quantum programming. It's not theoretical anymore. You can use a practical implementation, and also you can use the quantum computer. Okay, so any questions so far?
So in case we usually write we use the the eigenbasis, and we can write the Sx and Sy in the eigenbasis of the Fg. So is it Sd is built in this code, or we have to initially define that what eigenbasis we are using every time we write the code?
Okay. So to answer your question, the only state that is predefined is 0 state, right? If you want to start with any other eigenbasis that are used for the plus minus, you have to initialize it. You have to give probability amplitudes, and then you have to initialize that cubic, and then you're gonna start with it, right? So in one function we have did set. We have gave us probability amplitudes, and we have created a superposition state, and now we are applying Hadamard gate on that. Yeah.
Can we do a corner for simulation?
Yeah, we can use it. I never used it, but you can use it. So I forgot in the starters that I didn't give my personal introduction. So I completed my MPhil with Sir Farhan. After that, I joined a European company and worked as a quantum team lead in AI, where I was working quantum machine learning algorithms. And I have 2 years of expertise in quantum machine learning algorithms, and I have developed a new hybrid algorithm in reinforcement learning and HHL algorithm. After that, I went to Netherlands, and for there I stayed for 1 year and worked on quantum key distribution. And right now I'm working with Sir Farhan and also another company as a team lead as well. So feel free, I hope you guys have my email and number. Feel free to contact me if you guys want to learn and have this program. Thank you.
Can I ask,
Yes.
so how many of you don't know Python? So you need to learn, because for next couple of days we need to know Python. And how many of you will not be bringing a laptop from tomorrow onwards? So all of you will be bringing your laptop with you? Yes.
Yeah.
Okay.
So if you guys are bringing laptop, I would send this to
Can we create one subgroup to show this?
yeah, we can create, and I'm gonna forward this, and also probably the tomorrow program as well. So we have the programs, and I'm gonna explain the programs, and we can do it together. Right, so we're gonna be doing some superposition, entanglement, teleportation circuits in real life and simulating it together. Right, so that would be it.
So can you make a WhatsApp?
Yeah, I can